I'm going to start the AI companion, and I'm going to start the summary, and I'm going to close out. So Miguel asks, are the slides up? Yeah, slides are always here at Mixtape Sessions, Causal Inference I, and they're under slides, and it's the known observed confounders. So we're going to be there again. Let me put that there. I'm going to put this in day 3, even though it was starting off on day 2. So here's where we are. All right, I'm gonna go ahead and yeah, I'm gonna go ahead and I will have to grab my iPad later. But so what we did, let me sort of summarize what we did. And I kind of feel like we went a little fast over correcting for selection bias. So I might just kind of real quickly review it. But what we did is obviously we did the DAG stuff to kind of illustrate the challenges of doing any kind of methodology that's using covariates. That's an easy way of describing it. Any kind of methodology that's solving the causal inference problem when you don't have an RCT just by using covariates. And that's kind of the most standard way, arguably, that people go about causal inference in the following sense. Most people in the world that have any stats training, whether it's undergraduate, graduate, or just even in industry that didn't take it, most of the time, what do? They run regressions and they put in controls. And it's just very standard. And whether or not they use the word causal inference, typically they're interpreting something in that as causal. Maybe all of it's causal, or maybe it's like one variable that's causal, but typically it's pretty common. And what we were kind of saying with this DAG stuff is we were like, well, there's nothing wrong with doing that. It's just that it holds under very specific assumptions, not any different than any other methodology, but any methodology is only valid insofar as the assumptions of the model are true. And the assumptions of the model, when you're trying to estimate causal effects with covariates, it's not things like, well, it can get into, we'll see, it will get into a bunch of, modeling assumptions like linearity and so forth. But at an even deeper level, it's saying you have the right controls. You have the right controls in there, and you don't have the wrong controls in there. You don't have the bad controls, the colliders. If you can satisfy that, then you can move into all this stuff. If you can't satisfy that, you can't move into all this stuff. And that's kind of the idea here. So what we did was, after we laid out those DAGs, and we said, we introduced this one theoretical concept called the backdoor criterion. And the backdoor criterion sort of showed the minimal but necessary, or rather, yeah, the necessary and sufficient conditioning set, or rather the necessary and sufficient set of controls that will allow you to identify the causal effect, or an average causal effect, of a particular treatment intervention. From there, we left the DAGs because the workshop really is not intensively. I had it open a few seconds ago. Okay, I'll look at it. I think I closed it, Miguel. Let me go ahead and give real quick the Discord. Invite people, because I know that not everybody is like super enthusiastic about the Discord, but you never know, because there's lots of good conversations that happen in the Discord. So so then what we said was, well, we're gonna oh yeah. So my reasoning of the value of the directed acyclic graphs, the directed acyclic graphs actually have a lot of value, but not everybody probably finds all of it useful. Okay. So one of the main things that makes it really helpful is it really is a great communication tool for explaining causal effects. And, no matter who I'm talking to, when I explain when I explain causal inference or problems with causal inference using DAGs, it's just incredible the universality of it being really meaningful and very helpful for people that are going from kind of not accustomed to a causal inference. Maybe they don't come from an experimental background, or maybe they do, but they're not used to thinking about the observational stuff or whatever. It can be really helpful. And then the second thing it's really helpful for is communicating assumptions. And then third, it's very helpful for this controlling for stuff. Okay. And so what we did was, once we sort of said we're going to use the DAG to come out with the conditioning set, I think everyone sort of had the same response, which is, where does the DAG come from? How do I know I have the right DAG? And all this kind of stuff. And, you know, one of the things I basically say is, well, if you are not confident that you know the covariates to include in the model, which is not something that I can teach you. That's something that really does come from your own expertise in your project, and DAGs can really help you sort of walk that through. If you are really uncomfortable with it, there's still stuff you can do, and we kind of looked through some like second best approaches that people will sometimes use to kind of get at, like, you know, this is as good as I can do, this is as confident as I can feel. And it was things like definitely controlling for confounders that you feel like you can name, definitely avoiding controlling for anything that's an outcome, and going through various falsification exercises to kind of give you some confidence that, yeah, that this might be plausible. That said, though, you should always be nervous about using the covariate adjustment, precisely because it does require a prior model. It does require some prior theoretical information about the data generating process. And frankly, a lot of us barely even understand what that means, let alone have confidence that we know the system of equations that determine all the variables in the data, especially since we're oftentimes working on things that people really don't even have a lot of prior knowledge of in the first place. That's why we're studying them. That said, though, the rest of the workshop on these confounder stuff was all about assume you do have the correct covariates, and let's move on. At that point, we sort of laid out our assumptions. We said, all right, well, let's move away from the DAGs, and let's talk about the statistical interpretation of the backdoor criterion. And that's where we introduced this term unconfoundedness, and sometimes you'll see the word ignorable treatment assignment as well. We used that Titanic example. We defined our aggregate target parameters, which were mainly average treatment effect, average treated on the treated, but we also talked about the average treated on the untreated, and we laid out the assumptions, the minimal assumptions that you need in order to identify those parameters. They were basically versions of the randomized experiment assumptions. They just were randomized experiments within the dimensions of the covariate set. That's very strong. It's very strong. It's very strong because the reason why you have confidence in the RCT assumptions, which were that the treatment is assigned independently of the potential outcomes, the reason that you had confidence in that is because the person running the experiment literally imposed that on the data. The reason why it's hard with the observational designs is that you're passive in the data collection, and you think that you know where those coin flips are happening in the data. That's hard to know. I mean, that's an understatement. That's hard to know. But the whole class is assuming, or not the whole class, but this part of the class says, I understand that it's hard. I understand that it's hard, but I'm going to assume that you figured it out. It's a whole other thing to figure it out, but I'm going to assume that you did figure it out. And having figured it out, we're going to lay out the other assumptions that you need in addition to unconfoundedness. And the other assumption was common support, which was that the distribution of the covariates were overlapping for the control group and the treatment group. Any kind of particular combination of the covariates, whatever that was, white, male with glasses, bald, 48 years old. There's guys like that in the treatment group. There's guys like that in the control group. As long as there's overlap, you can use that unconfoundedness assumption that you feel confident in and estimate these average causal effects. But then the question became, well, what's the method? What specifically is the method? Because defining the parameters and defining the assumptions that are necessary to identify those parameters is not the same as coming up with a model. And so then we looked at 3 models. Subclassification, an old weighting method, which actually, interestingly enough, is kind of a fairly paradigmatic approach to causal inference that we see all the time. This kind of weighted average of these particular observations to kind of get these average causal parameters shows up in diff and diff, shows up in IV, shows up in the rest of this stuff, even shows up in synthetic control. It's not always exactly like this, but weighted averages is really at the core of a lot of what we're doing in causal inference. Once you introduce that potential outcome stuff, you're automatically working with averages. And once you're working with averages, you're basically doing estimation by using various techniques to do weighted averages. And we're going to see even the regression is doing that. Okay. So then we did subclassification, which is not used, but it's kind of was the first, and it's, I think, very helpful. And then we went into exact and inexact matching. So today what we're going to do is propensity scores regression, and then we're going to go into simulations, and then we're going to go into instrumental variables. All right. So I want to go to review one more time this selection bias problem. And real quick, I see that someone has posted on general. Oh, okay. So we're going to look at this selection bias problem in the context of inexact matching. And like I was saying, just as kind of a review here, selection bias to most people means that you have selection on unobservables. What that means is you aren't controlling for the correct things. We are, though, assuming you are controlling for the correct things. But the curse of dimensionality means you almost always will fail the common support assumption, and it is just as important as the unconfoundedness assumption, which is the same as saying you have the correct covariates. So in the context of matching, you end up so often, if not every time, with not having overlap in the covariate set. Oh, thanks, Sebastian. Or thanks, Shreyoshi. Thank you. So not having overlap. And if you don't have overlap in matching, you have selection bias. But it's a particular kind of selection bias. It's matching bias. All right? It's matching bias. And what's nice is that matching bias is different from the bias caused by selection on unobservables, because unconfoundedness, as we showed last week, will allow us to come up with a bit of a correction, or what's called bias adjustment, that does work when common support fails, but does not work if selection on observables fails. All right. So that's a lot. I'm saying a lot right there, but I'm wanting you to kind of see that there's a lot of things that go into this bias in the context of matching, and we're going to kind of cover it all. So here we have, again, and I'm not going to go in as fast. I'm going to go a little bit faster because you do have the recordings, and some people probably did track really well, but some people didn't. And this bias adjustment method that we're going to look at, it actually is showing up more and more these days within the synthetic control literature. This bias adjustment method that Abadi and Embens came up with actually has turned out to be relatively influential. So we're going to look at it, and we're going to kind of remember that if you learn it here and you really understand it, it turns out to be pretty useful, all right, to even extend beyond it. And who knows how you might want to use it even in your own work if you learn a little bit more about, why it works and when it works. So here's our estimate of the average treated on the treated using matching. And what we have here is a treated unit matched with an untreated unit, but we're going to fail common support. So we're going to be able to match, but it's a nearest neighbor. And if you have unconfoundedness only holds at the exact match level. So if you ever go into inexact matching, even if you start bending the data to satisfy that matching, it doesn't satisfy unconfoundedness. It's just going to rewrite the common support assumption in such a way that, you can do exact matches, but you're paying a price for it because you're doing exact matching by nevertheless matching units that are technically dissimilar. But that doesn't really mean the bias is large. A lot of this, or all this, has to do with how much heterogeneity you have in the treatment effects, how they vary with respect to those covariates. If they don't vary very much, it's not going to be harmful. But if they do vary a lot with respect to those covariates, then automatically it's not going to match well, and that's going to introduce bias. So here we have an inexact match. We're going to write down these potential outcomes. Mu1 of x, mu0 of x. And mu0 of x, let's kind of work our way backwards here. We say under the treatment assignment, we're going to say mu of 0 is equal to expectation y0. So that's all this is. It's the average y0 overall, okay? X equal x. But we only have data on y0 for the control group. Right? We don't have it for the treatment group. It's counterfactual. So we're going to rewrite this. And actually, now that I look at it, it might actually have been better to go in the verse order. Maybe I did it for a reason. So we're going to write that down, and we're going to do the same thing with mu1. And we're going to say that the realized outcome is basically based on the potential outcomes and whether or not it's treated plus this error term. And this is called an outcome regression model. Now, there is some assumptions buried into this, which is you're going to do this selection bias correction, but you're going to have to use an outcome regression in order to do it. So then we're going to substitute distribute the terms. There's y, there's way ji. We're going to substitute in those potential outcomes, and then we're going to rewrite it. All right, we're going to rewrite it. So even though that's mu1 and that's mu0, and if you look back, mu1 is y1 and mu0 is y0. So technically, y1 minus y0 is causal, but this right here minus that right there is not causal. It's not causal under this because, if we don't have this correct match, because it's supposed to be x equal x, but we're saying we fail common support. So when we did this, it's not the perfect one. So it's not technically x equal x. It's not technically x equal x, okay? So then we write it down. And so then right here, we write down the bias expression. We're going to say, well, that's our estimate of the ATT, and that's the true ATT. So I'm going to put that in there. And that's what we had just a second ago. And then I'm just going to add in, a couple of terms. I'm going to add that in to this. All right. So when I add those two in, look, I got average y0, the average mu0 of x, I, this is counterfactual. For group I do not observe their Y0. For group I only observe their Y1. That's it right there. See, Y1 for XI, there is no mu1, there is no mu0. That's not mu0. That's mu0 with respect to J. This is so I don't actually observe mu0. So how did I get it? I just added in a 0 that was equal to that term minus itself. When I rearrange it, look what I get. That's the average treated on the treated right there. Mu1 for X, mu0 for X. It's unobserved, but that's okay because what we're doing is trying to derive the bias. Then we go down here. So we look at this like scaled by n or this average here. Well, rather it's the 1 over n times that bias term, taking the square root. Take the average of that. Okay. And what we've got here is this like situation where in the asymptotics, as n goes to infinity, it's biased or it's unbiased. And the reason why as n goes to infinity, that this term right here has no bias is because as n grows to infinity, you always will get common support. The common support problem is caused by, yeah, it's for the whole thing. It's for the entire thing. Sorry, I don't really know why. I'm not really know why. I believe it's for the whole thing. It's a good question. I believe it's for the whole thing, but now I am kind of wondering. I haven't thought about this in a while. I'll find out. I'm a little bit, I need to check. But this is kind of a, exactly. That's it, Akish. As n grows to infinity, there is no curse of dimensionality. So as n grows, because that's the idea. The reason why there is no exact match is always expressed as you're working with a finite sample. It's too small. It's too small. Why? Because the dimensions of the covariates are so large, right? We had this like, as you had 10 variables, each of which had 3 values, there were 50,000 dimensions to the data. So if you have a data set that doesn't have like 100,000 at minimum just to have treatment and control, even that's like, even at 100,000, that was how many observations you would need. And that's still not going to be enough because it's all random. So you're still going to have missing cells. So, but if you go to 1 million, if you go to 2 million, if you go to 1 billion, you'll have it. But what if you had 10 variables with 5 values? What if you had a continuous variable? Then it's like really, then you're like, it's only kind of in fantasy land that you can get exact matches because n has to grow to infinity. So, but what's kind of interesting is that you're right, that's interesting. But in reality, I'm not going to have that. In reality, I'm not going to have that because even if I'm working with 100,000 observations, still finite sample, and that's a gigantic data set, it's still a finite sample, and you'll have inexact matches, even with something as trivial as 10 variables with 3 values, which what is that even talking about? So this is what all this is about. This is this convergence problem. So the difference between these two, to go on what Akish said, so as n grows to infinity, we'll get an exact match, but it's converging, and it's converging slowly. And as a result of this converging slowly, the average Y0 also converges slowly for the treatment group and the control group. And this may never, for the treatment group, this may never converge to 0, and it can be very large. And this right here, the bias may never converge to 0 too, which means that even in the very, very large sample, even though you have this convergence issue going on, it is converging as n grows to infinity, but it may be that you still have large selection bias matching bias in the data, but you'll never know. You'll never know if you have it because this term right here is unobserved. Rather, that right there is unobserved. Okay. So if that's the case, it's entirely possible that you have extremely large bias, and it's all because the matching discrepancy is sort of larger than the estimated treatment effect. And so this matching bias really does need here's the thing. In order to use this matching estimator, you're going to need to check to do exact matching. You're going to need to check whether or not you have exact matches, which you're not. And then you're going to have to see you're going to need a large control group. If you're estimating the ATT, you're going to need a large control group. A lot of people use this matching estimators and they don't really understand this stuff. And so they'll use it with small data sets and that just won't work. Okay, it just won't work. So first of all, the matching discrepancies are observed. You can see the degree to which you have that matching discrepancy. You can check it in the data. It's a little work, but you can do it. The way that you get this to be unbiased is to create a very large reservoir of untreated units. But, you know, the thing is, that's like kind of wishing away the problem because most people are just working with the data that they have. But if you have it and you don't have the large data set and you do have matching discrepancies, then you can use what's called bias correction. We're just going to review it again. So here's the thing. That's the bias. You don't observe this, you do observe that. Because you do observe this, because that's a control group unit. And for all the control group units, you observe Y0, and that's all that is Y0. It's just that you don't observe Y0 for the treatment group. So what you're going to do is you're going to estimate Y0, which is allowed. It is allowed. It is allowed. It is allowed to estimate Y0 for the treatment and control groups because under unconfoundedness, expectation Y0 d equal 1 x equal x equals expectation Y0 d equals 0 x equal x, okay? So whatever the relationship is between X and Y in the control group, because Y equals Y0 in the control group, that's the exact same relationship between X and Y0 in the treatment group. So if you can estimate a model of Y onto X in the control group only, get those coefficients, and you can predict Y0 for the treatment group under unconfoundedness. And I don't know, it's weird. That had never been done before. That had never been done before until this Abity and Embens paper in 2011. I think it's Journal of Business and Economic Statistics. I don't know why I didn't go into econometrica, but it's that's where it ended up. So let's look at it. Okay. It's an outcome regression model. All right. And outcome regression models have assumptions that you're going to be assuming this linearity of Y0 as a function of X. Okay. But put that aside for now. You're going to regress Y onto a constant and all of the covariates. All right. You're going to assume you have the correct specification. You could interact them. You could do whatever, but you're going to do that. And then you're going to get estimated coefficient beta, estimated coefficient alpha. And remember, under unconfoundedness, okay, under unconfoundedness, whatever that relationship is for the control group, it's also the same relationship for the treatment group. So once you have those coefficients for the control group, which can be estimated for the control group, those are the same coefficients for the treatment group. All right. And this actually does show up, interestingly enough, in these new diff and diff papers. Borisak et al. is kind of doing something like that in their robust diff and diff estimator. And Kyle Gardner's kind of doing something similar too, except his is a little different. So, and even in the old Heckman, Ikamura, and Todd paper from 97, which was an outcome regression model for diff and diff, that's what they do too. This is like, this is done. This is done. It's bigger than it looks. It's very common. So once you get it for this, for the control group here, you got the same thing for the treatment group under unconfoundedness. You're going to then delete off the difference of the two. You're going to delete it off for the difference of the two from each of those individual treatment effects that you estimated, because this was the source of the bias. That was the source of the bias. Because if you go back, think about what the source of the bias was. There's the treatment effect. There's the ATT. And what we did was we showed that when we subtracted out the ATT from that, the only thing we were left with was that. So that means that since we can estimate that, we're just going to plug it in right there, and it becomes unbiased, as long as that outcome regression model's specified correctly. So that's what we do. We delete it off, and then we calculate this Abadian-Imbens standard error, called the Abadian-Imbens robust standard error, or AI robust standard errors. And that's it. Does anybody have any questions before we move on? Akish has the question, so I'm going to put him here. I actually kind of feel like, to be honest, I think that is one of the coolest papers. And when I really started studying it and figuring out what it was really doing, and I started seeing how it flowed right out of that unconfoundedness assumption, it really makes you kind of go, wow, we're using so often. Well, no, if you don't have unconfoundedness, Akish, if you don't have unconfoundedness, then you shouldn't even be doing the matching in the first place. Because if you don't have unconfoundedness, your bias is not from the mismatch. Your bias is from from those unobservables. Okay? So you're not solving anything with covariates if you don't have unconfoundedness in the first place. So yeah, if you don't have unconfoundedness in this matching scenario, then you're not correcting for the correct bias. You're just correcting for the matching bias, which is not the same thing as the unconfoundedness bias. Share the link. Yep. Right. Absolutely. So we're looking here at known and observed confounders. There you go. And what we're on is slide, right now we're on slide 143. 143. Exactly. Step one, probably actually step 0 would be, be confident about unconfoundedness. That's the first step. For whatever reason, you're confident. The next step is, see if you can do exact matching, because it's non-parametric and it doesn't require making assumptions about a regression model. Secondly, if it doesn't work and you don't have exact matching, you're not, then you can go to then you can go to these inexact matching. All right. And what you get from inexact matching is this bias adjustment method, but it will have an outcome regression model inside of it. And so, we're going to kind of talk a little bit more about that. But yeah, that's it. That's it. Okay. Does anybody else have any other questions before we move on? I think this is a very valuable method. I think it's something that you put in the toolbox. Oh yeah, sure thing. Inju is talking. Let me put you over here. Exactly. That's exactly what I'm saying. And I'm glad y'all are asking these questions because it shows that it's starting to click. Exactly. If you have selection on unobservables, propensity scores, regressions, matching, inexact matching, subclassification solves nothing. It doesn't, well, it solves, okay, it does solve some things. It solves the mismatch. So the degree to which selection on observables is really the driver, it would fix that. But, you know, you'd have to be pretty confident. There are methods for testing the degree to which selection on unobservables is holding. I did an interview with Chris Tabor on this week. And Chris Tabor has this paper on no, that's not it. He has a paper. Come on, what's the deal here? Oh, it didn't come up. So it's Tabor, Elder, and Altanji. Here, look, Altanji. This was in 2005 Review of Economics, 2005 Journal of Political Economy, Selection on Observed and Unobserved Variables, Assessing the Effectiveness of College Catholic Schools. And they say this, and I apologize, this is kind of small. So they say this is kind of a classic paper. It's been cited like 4,000 times. And they say, in this paper, we measure the effect of Catholic high school attendance on educational attainment and test scores. We do not have a good instrument for Catholic school attendance. So we developed new estimation methods based on the idea that the amount of selection on the observed variables in a model provides a guide to the amount of selection on the unobserved variables. We also propose an informal way to assess selectivity bias based on measuring the ratio. And then I don't have it, but and I'll post that. So that's like a paper that people do. There's also another one that Emily Oster has written called Unobservable Selection and Coefficient Stability Theory and Evidence. And I'll read this one. Common approach to evaluating robustness to omitted variable bias, right, which would be selection on unobservables, is to observe coefficient movements after inclusion of controls. This is informative only if selection on observables is informative about selection on unobservables. So that's like a very special case of this kind of selection on observables. Chris Tabor, in my interview, he kind of elaborates a little bit on it. He says, you know, if you assume that the selection on unobservables is the same as the selection on observables, then our technique will work. And that's but that's a very strong assumption. So Emily Oster says, she says, although this link is known in theory, very few empirical papers approach it formally. I developed an extension of the theory which connects bias explicitly to coefficient stability, which is not what they did. I show that it is necessary to take into account coefficient and R-squared movements. I develop a formal bounding argument. I show 2 validation exercises. And then there's one more, Carlos Cellini, Washington Statistics. This is Carlos Cellini. I interviewed him also. Okay, let's do something. I'm gonna do that. Carlos. Dadgummit. University of Washington, Department of Statistics. Pearl. Maybe that's it. Carlos Cinelli. That's it. So Carlos Cinelli has a paper. So that's the paper that I wanted you guys to read, A Crash Course in Good and Bad Controls. Let me find it. Here we go. So he's got a paper called Making Sense of Sensitivity, Extending Omitted Variable Bias. And here's what he says. We extend the omitted variable bias framework with a suite of tools for sensitivity analysis. in regression models that does not require assumptions about the treatment assignment nor the nature of the confounders. So that's different than that Altanji, Tabor, and Elder paper, and that's different from Emily Oster's paper. Handles multiple confounders acting nonlinearly, exploits expert knowledge, this is that DAG stuff, to bound sensitivity parameters and can be easily computed using only standard regression results. And he's got an R package, he's got a Stata module, he's got a Python package, he's got a Shiny app. So let me give you this real quick. 2. Okay, thank you, Mauricio. Okay, so Anna asks, how is matching bias different from selection on observables? So selection on observables, right? So that's very helpful. So selection on observables is just another term by Heckman and Robb, 1985, right? It's this paper. I don't remember what it is, but I think either it was a paper or it was a chapter in a handbook. Selection on observables is just another term by Heckman and Robb to describe unconfoundedness. Okay, and unconfoundedness is this: y0, y1, d conditional on x, which means given x, all remaining variation in d is independent of the potential outcomes or as good as random. Okay? This is the core assumption of using covariates to estimate aggregate causal parameters. We can call this assumption 1, selection on observables, or unconfoundedness. All right? Everything we did on day 2 and today so far assumed unconfoundedness. So therefore there was no bias that comes from not having the correct controls. Okay? The second assumption, though, is called common support. And common support says you have at least one observation in both treatment and control for all dimensions of X, meaning their interactions. Okay? That does not ever hold in finite samples with even a relatively small number of covariates or one continuous variable. Because for a continuous variable, you'll have, values that are, trailing, digits. And you need exactly, the same x equal x in both treatment and control to satisfy common support. So in a finite sample, but not in the infinite sample, in a finite sample, the so-called curse of dimensionality will happen, and it happens really quickly. After only a few covariates. And it just means your data set is too small relative to the dimensions of X and the impact that that's having on common support. So what we said was, unconfoundedness and common support are two separate assumptions. They're two separate assumptions. You can have selection on observables, unconfoundedness, and still not have common support. And if you don't have common support, you have matching bias, even though you don't have the bias associated with selection on unobservables. It's two forms. The matching bias comes from, matching discrepancies. I matched a 48-year-old white man with glasses with a 45-year-old white female with glasses. If the treatment effects are slightly different or largely different for those two groups, then even if the only variables I need are age, race, sex, and eyewear, it'll still be biased from matching, the wrong units, but that might be the best you can do. Okay, so that's kind of that's what it's about. That's what it's about. That's what it's about. So, yeah, Pappy got it. And then Eduardo says, no, it does not imply the balance of covariates, Eduardo. It implies a non-zero probability of being in the treatment group and the control group. Well, it's rather this. The probability of being in the treatment group and the control group is bounded between 0 and 1, but not 0 and 1. It just means that you have somebody to match with. Okay, you have somebody to match with in both. So it doesn't imply balance. Unconfoundedness is going to sort of, deal with that. You just need overlap. Exactly, Miguel. Regression, as we're going to see, does not require common support, but it requires something else. It requires something else. And we're going to see in a simulation that it matters. Okay. I see as Shika's typing, so we'll look at that. It's cool that he made a Stata module. T. What was T? Oh, it. When you say there was someone to match with, it refers to exact matching. Yeah, it refers to exact matching. And so what we said, Ashika, is that, when you move into the realm of inexact matching, whether it's propensity scores or nearest neighbor matching, you'll kind of like do your best. Okay. Unconfoundedness will, let's say you're basically like, assume unconfoundedness does hold, but unfortunately I have the right covariates, but there's not enough data to do the exact crosswalk between the treatment group and control group. All right. So you go, I have exact matching. Sorry, I have unconfoundedness, but I have inexact matching. How big is the bias? Bias might not be very big. The less heterogeneity you have in the treatment effects, the less relevant common support even is. If the treatment effects are literally identical for everybody, you don't even, common support ends up being not a big deal. But the more you have, the more that you have heterogeneity across the covariates, any of those inexact matches, depending on the number of them and how big they are and how big the weights are associated with it, it can really introduce some problems. So in this realm, we have with bias adjustment or bias correction, the ability to kind of deal with it, or at least somewhat. Well, common support, I'm going to do it right here. I'm going to do common support in just a second. Common support just means that there are units with the same values of the covariates in both groups. Covariate balance means the average of the covariates are the same in both groups. So it's, I guess, if you have exact common support, I think that exact common support means that the covariates will be identically balanced. So let me Moshan, let me think a little bit more about it. Common support, I want you to be thinking of common support primarily in terms of the overlap assumption of I have units with all values of X in both groups. But if you did have units with all values of X in both groups, I gotta think about that a little bit. Does that mechanically imply covariate balance? It might actually impose it. You have it, but I need to think about it because I'm thinking to myself, well, if I've got literally, one of each of these groups, it's just that covariate balance is not really with respect to the dimensions. Usually it's a table. Treatment group, control group list each covariate, but not necessarily their interactions. And that's the part I'm not exactly sure about, because we're not saying that you have men in both groups, 48-year-olds in both groups, bald people in both groups. We're saying you have 48-year-old men who are bald in both groups, 48-year-old women who are bald in both groups or in neither group. It's more intensive than just looking at a table and seeing if they're balanced. You could have the means different linear, like with respect to each covariate, but in the dimensions is what we're really talking about. I'm not sure I understand, Allie. Only covariant confounders that affect the treatment. All right, so Pappy's going to talk here, and then we're going to take a 15-minute break. Yeah, matching is very popular. Matching is very popular. Subclassification is not as popular, and I don't really know why, but subclassification is basically a form of weighting. And, as we saw, subclassification runs into the curse of dimensionality. And when you run into the curse of dimensionality, the question is, are you going to even attempt to get that estimate? You can't do it with subclassification, but, with these other methods, you can still get estimates of those aggregate causal parameters. They just might be biased. Subclassification won't even attempt it. It won't even attempt it. It's like if you don't have exact matches in subclassification, it can't even try to do it. Whereas nearest neighbor matching and propensity score matching, it'll try to do it. And with nearest neighbor matching, it'll actually go a little bit further and give you a method for bias adjustment. Yeah, they are. All of this is covered in the book. I think that's probably true. You're doing it with respect to the moments. Well, is it matching the distributions of the covariates? It is, Pappy, if the distribution of the covariates implies that even in the interactions, that's the part I'm just not 100% positive about. If mechanically what happens in one dimension happens in all the dimensions. That's the part, that I'm not entirely sure. Or what happens with respect to the K variables happens with respect to however the notation would be for all dimensions. So if the mean of each covariate is the same for treatment group, does that mean that there is non-zero number of units with the exact same that are that are there in both groups. That part I'm not positive about. And I'm sure, and I'm sure there's a known answer. And so I wouldn't be surprised at all if it's like, yes, that's what it means. But I don't think it means it. I don't know if it holds with the average just of the variables. That's the part I don't know. Jeff, I see you typing. These are all great questions though. Every time I teach this, nobody in the 1,000 times I've taught this has literally never been asked, so I haven't thought about it. But I'll start thinking about it. It's a race between Jeff and Miguel. Who's going to hit enter first? Miguel dropped out. All right. Well, listen, Jeff, while you're typing, I'll answer your question when we get back. Let's take a 15-minute break. Come back at 11 minutes on the hour. So come back in 15 minutes. Okay. So, let's do a simulation. I was just thinking we should do that right now. So I didn't even think about it. If you could go ahead and pull the most recent copy, I changed some stuff and I want to show you where we are. So let's mixtape sessions. All right. So Causal Inference I, labs. We're going to be here in matching. Okay. So we're going to pull up matching RA. We're going to use this one a few times, matching RA. I don't have the R version, and I'm going to explain why in a minute. But let me walk you through what we're going to do before we move on. All right. So I'm going to have 5,000 observations, and I just kind of arbitrarily pick a cutoff where the first 2,500 are in the control group, and the second 2,500 are in the treatment group. I'm going to have two variables. They're both going to be continuously distributed, which is going to necessarily violate inexact or common support. But what we're going to see is that nevertheless, we have unconfoundedness, because you can see here when I assign people to the treatment, it's got nothing to do with age and GPA. So I'm going to run that. All right. And I'll show you what common support doesn't look like. But you can see here how I imposed the problems of support. Treatment group on average is 25 with this variance of 2.5. But for the control group, they're older with larger variance. In their high school grade point average, those are not from the United States, GPA means their grades in high school, more or less. And for the treatment group, they did worse than the control group, right? So the treatment group is older and it has worse grades, is the idea here. So we run it, and then we're going to look at a histogram to kind of illustrate one by one the overlap. So you can see right here, there is some overlap issues. So the treatment groups, we've got units that are young here, and oh, the control group is older. I was wondering. Control group is older, treatment group's younger. That's what it is. And then the treatment group has worse grades. So these guys are younger. So you can see right here, we've got people in the treatment group as young as like 15. Nobody in the control group is that young. And we've got people in the control group that are almost 40, and nobody in the treatment group is that young. So we've got some overlap, we have some overlap. So let me just kind of draw that. So we've got some overlap, but the overlap is really like right here. And but it's even more difficult to really understand than that because these histograms are bending it. So, you know, there could be spotty overlap issues all in here, but we can definitely see we have overlap problems over here and over here. All right. So we run it again on GPA. And there the overlap's not as bad at the tails. Okay. So we actually have perfect overlap for the treatment group. So like everywhere, here's how we interpret it. So we say like, you know, here's the treatment group's lowest value. There's the treatment group's highest value. And within that range right there, okay, within that range right there, I've got a distribution of treatment group values by GPA, and I've got a distribution of control group values right there. So any overlap that I'm needing to estimate the average treatment on the treated, I'm going to have it with respect to that one covariate, but I just don't have it with respect to the other. And if I'm trying to get the average treatment effect, then I won't, because the average treatment effect needs more than that. The average treatment effect needs it for the control group too, and I don't have any treatment group units here, and I don't have any treatment group units there. So, you know, you can have overlap with respect to one group, but not necessarily have it for the whole group, okay? All right, so I'm going to do something. I'm going to recenter the data. That's something I got to do for a later thing that I'm going to do, but I'm going to recenter the data, and I'm going to create some polynomials. All right, I'm going to create some polynomials, and I'm going to have this. These are the same thing. I don't know why I did that, but so you could just do the same thing. UGA, ACUS, you could do the same thing. You could also do stuff like this: by sort treat, sum, age, GPA, and that would let you kind of see here for the treatment group, you know, minimum values of -12, and for the control group, it's a -7. So you know you don't have overlap there. And for 6.6, 12.2, you know you don't have overlap there. So like you could do it, you know, manually there. And there's nothing about a dummy that you couldn't still look. You know, you'd see if you have any zeros, if you have any ones. Okay. So look what I have here. I'm modeling the potential outcomes in this simulation. I'm not just like modeling a realized outcome, modeling the potential outcome. So I'm saying, well, the potential outcome is going to be a linear model. All right, it's going to be a linear model. So it's going to be equal to 15,000 plus a 10.25 on age, negative 10.5 on age squared, 1,000 on GPA, negative 10.5 on GPA squared, 500 on the interaction, and then an error term. Okay? And then I'm going to have Y1, and Y1 is going to be this whole thing plus a 2,500 plus heterogeneity in the treatment effect. So I've got, if you're treated in a world where you were treated, then your Y1 value is going to be all of this plus a 2,500. And then there's like additional variation in Y1 from your covariates that's like different in a world where you're treated than in a world where you're not treated. All right. So I'm going to generate that, and I'm going to generate my treatment effects. That's what I was saying, Robinson. I can delete that. I didn't want to delete it right now because probably, yeah, it looks like I'm using it down here, but it's the exact same thing. You can see it's the same thing. It's the exact same thing. I must have had some carryover. Because I did this. Sorry. This is the part I was kind of saying. I demeaned the data. I recentered it. I recentered the data so that the average is 0. You have to do that for a particular method. Yeah, I know. I kind of went through it fast. I forgot that it was there. This is a last minute decision to do this. I usually do everything at once, but I actually kind of think it would be helpful to do this. So I've got here the treatment effects. So look, the average of the treatment effect is 2,500. That's coming from this, all right? So if you basically have the mean of Y1 is 17,688, and the mean of Y0 is 15,188. And this is why, Shreyoshi, I demeaned it, because the mean of age once it's recentered and the mean of GPA once it's recentered is 0. So when you do that, you get 2,500. That's coming from here. Okay, so the average treatment effect is 2,500. But what's the ATT? $19.77. What's the ATU? 3,022. So we've got like heterogeneity in the treatment effects, and it's heterogeneity with respect to the treatment and with respect to the covariates. All right. So I'm going to do that. That's our switching equation. We're going to now have our outcome. And now it's as though we don't have that. All right. So let me just kind of show you a spoiler alert of, even though we've got unconfoundedness, we're going to see now that the regression model is wrong. All right. So notice I ran regression onto treatment, age, GPA, age squared, GPA squared, interaction. All right. Which was age squared, GPA, GPA squared, interaction. Okay. And it's a linear model. It's just that it was linear with respect to Y0. But see, it's not like when you've got heterogeneity with respect to the covariates, it like screws up the regression. And we'll get into more of that, okay, why that is. But notice, that's not a 2,500. And that's not a 1977. So, in fact, the OLS model was biased. It gave you a 2375. I don't, Eduardo, and I'm going to show you why. In just a second, I'm going to show you why. But you could create it pretty easily right here. And some of this you can create, but there's going to be one thing that I haven't figured out how to do it in R, because the package is, I'm not positive it works. I'm going to explain it in a second. So in Stata, the ability to do the nearest neighbor matching is a canned routine called TFX. It got folded into nearest neighbor matching, like, I don't know when it was. It was like Stata 12 or something like that. And but it was originally a program that Abity and Embens wrote with someone else. So we're going to run it. We're going to do the Mahalanobis distance minimization on the average treatment effect. But we don't have overlap. And we have heterogeneity with respect to the covariates, and I'm only going to match on this. And I'm going to minimize the Mahalanobis distance. Average treatment effect is 2,500, and I get 2,200. So you see here, the nearest neighbor matching is not working. Nearest neighbor matching is not working. Well, the covariates don't matter for interpreting any of the coefficients. They don't matter. They're just used to satisfy anything. But in fact, demeaning it's not going to change the interpretation, because it'll still be a 1-unit change in each of them. So when you demean them or not, it doesn't really matter for interpretation. It'll still be a 0. It'll still be a 1-unit change. And it's a 1-unit change whether it's demeaned or not. Because the mean is a constant. And so it'll change the constant in a regression, but it won't change the coefficient. You could do it actually and see, but it won't matter. So you can see right here, it's biased for the average treatment effect. What about the average treatment effect when you do the bias adjustment. All right. What about when you do the bias adjustment? Then you get it back. 2,500. AI robust standard error, 44, 43. But when we use the bias adjustment, we get a 2,500, which we didn't get here, first of all. And it's not really clear what parameter that's supposed to be estimating in the first place. So now let's do the average treated on the treated. We know that the average treated on the treated is a 1977. Let's do it controlling for those variables, all right? Controlling for those variables, but not doing any bias adjustment. It's supposed to be 1977, and it's not. Okay, it does contain it, but it's not the right number. Now let's do the bias adjustment. Gets it. All right. So what is the command in R to do this this method? So what we want to look at here is nearest neighbor matching Abity-Embens. Now, here's the problem. Look, nearest neighbor matching, also known as greedy matching. It uses the propensity score or it uses the Mahalanobis distance. But I don't think it's the Abity and M. So I think it is that's interesting. So I think that it is the same thing, but the fact that it does not cite Abity and Embens has always given me a little bit of some concern. Ah, there it is. Okay, large sample property. So I think it must be right, but it's not giving us the selection bias adjustment. The selection bias adjustment is 2011. So and so I've had trouble figuring it out. I can't quite find it. I think it's called, I thought it was called, let's call it, bias correction. Let's see if we can find it. Somebody texted me. You can play around with that, Renz. You can play around with it and see what it is. That would be probably a good thing just to kind of explore. Yes. If you're estimating the average treated on the treated, it'll estimate using the control group. Well, if you're using the average treated on the treated, if you're using the average treated on the treated, it will use I don't know why it's doing that. That's a good question. Oh yeah, it uses everything. So it's using the treatment group and the control group because it's matching to the control group, but because of but I don't think it's probably using all those. It's a good question. I don't think it is. I don't think it is. And what I'm not positive, there's a lot of stuff buried under the hood here that I think you can go in and like figure out the exact match and stuff like that. Like which ones got matched, but I've never really dug into it. So I don't really know how to recover which ones are being matched, but I think you can, but I don't think it is doing all of them. So I don't really know why it's doing that. So here's the deal. I'm not, I have not successfully found, I haven't been able to find it in R. But it's not hard to do. You could do it manually. It's just an outcome regression model. You could do it in R manually, run the regression, get the coefficient, run the regression on the control, get the coefficients in, predict the outcome, and then drop it, one by one. But the problem is you got to know, you got to assign that correctly to which ones are being matched. And that part, I don't really know how to do it. So like I haven't really seen it. Here, okay, so you want to see it? Let's do it real quick. So here, I won't demean it. Oh, I did something wrong here. Oh, it's gonna take me a while. Something, yeah. So I can't mess around with it because I have to. It's all this. It's all changing even the definition of the average treatment fact. So, yeah, I'll have to mess around with it, but it's changing it, but it's changing everything when I demean it. So I gotta mess around with it. But okay, okay. So doing this in R and Python, I really just can't seem to find it. And the only thing you really have, and I don't know why it's not been incorporated, except that it might be a little challenge. Maybe it's computationally hard to figure it out how to do it. But that's it. That's it. You can kind of see here that that regression, though it had the right covariates, that's kind of the interesting thing here. Though the regression had the right covariates, okay, probably if I demeaned it after, probably if I demeaned it after I did this, that would probably work. After I ran it, did it, got a treatment effect. But then, yeah, it's okay. Anyway, so even though like I got age squared, GPA squared interaction, okay, and I have age, GPA squared, GPA, all that stuff interaction, and I have the same controls. You see that? I have the exact same controls. Oh, you found it, Jeff? That's what I thought it was called. I thought it was called matching, but I was having trouble finding it. Hold on. Jeff thinks he's found it. So that was literally what I thought it was. Oh, it's a Chrome extension. I thought it was called matching. That's what I was typing. Yeah, I think that's right. Seekin's book. Seekin. Okay, or second. So let's look at that. So Abity. Where's it doing it? Oh, page 16? Okay, hold on. Bias adjustment. But see, it's doing the propensity score. But then did it also say mononomous distance? You're gonna have to dig into it. You're gonna have to dig into it, guys, on that. I'm not positive uh what's going on. I don't know why it's like, see, Abney and Imbens literally wrote it in Stata back in like 2002 or something like that. Paper wasn't published till 2011. I don't know why it's not been picked up but it's like, it's a very powerful method. And I don't, but maybe if you've got some kind of bias adjustment here for, this is going to do regression adjustment. Yeah, it's just, I mean, there's just like, that's not the same thing. So I don't know. I'll have to dig into it a little bit. I'm going to save it. Okay. So let's go into the propensity score now. All right. Let's go into the propensity score. And if something comes to you and you want to go back to it, just make a question. Okay. So the propensity score as dimension reduction, I'm going to kind of go a little bit faster through this, is developed in 77 and then Rosenbaum and Rubin. The Rosenbaum and Rubin is the big one. I mean, it's basically an exploding citation count. If you look at the full history of the propensity score paper, it's the second most cited paper in the history of Biometrica. I mean, it's got like 40,000 sites or something ridiculous. So if you've got unconfoundedness, what they show in the propensity score paper is if you've got unconfoundedness with respect to the covariates, then they have a proof that shows it's also with independent with respect to the propensity score. And what that means is if you've got a lot of covariates, you can just turn it into one covariate and the same assumption carries down. So any kind of computations that you're needing to do with respect to any kind of computations that you're needing to do with respect to the covariates that might be really complicated to do, you can carry it over to the propensity score. And once it was carried over to the propensity score, there were even new methods that you could do that were a lot more computationally easier to calculate than was true in those old school, those historically old matching methods. Like, you know, with those old computers, it was really hard to do the algorithm for the matching on the Mahalanobis distance when you had a large number of covariates. Okay. So there's a lot of ways to do it. I'm just going to focus on weighting and matching. Okay. So what you're going to do is once you get the propensity score, one of the main advantages of the propensity score is that once you get it, you can just use simple methods to evaluate overlap. And those simple methods are like going to be a lot more robust than what we were doing here. So like what we were doing here to assess overlap was we were going one by one. We'd look at it with respect to age. We'd look at it with respect to GPA. What we're going to do now is we're going to go and estimate the propensity score. And it's going to go like this. Step one, estimate the propensity score. It's going to be logit, treat, age, interaction. Step two, estimate the propensity score. Sorry, predict the propensity score. That should have been estimate the probability of treatment. Okay. Right. So I do that. So I go predict p-score. Right. And so now what do I do? Now it's as though I'm looking at age and GPA simultaneously. And that's the propensity score. It's both. Either one works. You just don't want to use OLS. OLS will be correct on average, but it's linear, and so it'll like spit stuff. OLS will put stuff over here. You know what? That might actually be interesting. So drop p-score, regress, probability of treatment, get the p-score. Notice how probability of treatment goes from 0 to 1 when I use the logit. Now I got probabilities of treatment going over beyond 1 and less than 0. And the reason why that's kind of silly is because the propensity score is literally a probability. And the law of total probability says probabilities can't be greater than 1 and they can't be negative. They have to be bounded between 0 and 1. They can be 0, they can be 1, but they can't be greater than 1, they can't be less than 0. You can't have a negative probability of getting a pair of aces, right? You can have it be low, but it can't be negative. That doesn't make any sense. And then the law of total probability says that all the probabilities have to sum to 1. So OLS is not recommended, but Probit and Logit have that property of like not allowing the prediction to go from 0 to 1, okay, go beyond 0 and 1. So it's easy to do it. So what's nice about, and let me, so what's nice is part of the value of the propensity score, which people don't really appreciate, but because they're so focused lots of times on propensity scores not satisfying unconfoundedness, they think, well, I don't think I have selection on observables. I think I have selection on unobservables. And well, then correct. If you don't have selection on observables, you shouldn't be doing propensity scores, and you shouldn't be running regressions. Nobody ever seems to be bothered by that, though. So so you you can evaluate common support. It's a lot easier. All right. There's an example: age, GPA, propensity score. Captures all of them at the same time, and we can see the degree to overlap that we have on the one dimension, rather than doing them all at the same time. It's a little bit confusing to navigate all the propensity score methods because there's a bunch of them, and then even within each one there's like even more. Okay, but they can really be summarized in two ways: matching and weighting. That's it. There's matching methods and there's weighting methods, and there's like advantages of each of them. So there's a variety of techniques also. The logic of it. What do you mean? What do you mean, Sergio? No. Probability of propensity score, probability of treatment. It's not probability of propensity score. It's the probability of being in the treatment group given that you have these covariates. All right. So we'll get to that in just a second. All right. We'll get to that in just a second. You want overlap. You want overlap because what you need for any of these methods that we're reviewing, you need for unconfoundedness and you need overlap. You need both of them. Okay. Well, you're not assigning the probability to being treated. You're estimating the probability of treatment. You're estimating it. It looks like this. Okay. I don't know if I can do it on the fly. I don't know if I can do it on the fly. So propensity scores are frequentist concepts. You basically say, I have, all right, let me think. 1,000 observations, 1,000 observations, 250 males are in treatment group, 150 female males are in control group. Sorry, 150 females are in treatment group. And there are 400 in treatment. Let's just focus on that, all right? Ignore for a second the control group. So it basically goes like this. Assume I pulled out of the data no, I got to do the whole thing. So I got to do the whole thing. So okay, so you say, it's like this. You basically say, I have 1,000 observations, 250 males are in treatment, 200 males are in control. 150 females are in treatment, so that gets me to 450 plus 150. So 450 plus 150, 550, 600. So that 400 females are in control. All right, so that seems right. So it's 250 males plus 200 males. So I got 200 plus 250 plus 200, that's 450. Plus 400's 850 plus 150,000. So there are, all right, so there's 400 in the treatment group and 600 in the control group, right? Okay, now assume this. I pull a random person out of the data and it is a male. Okay, what is the probability that that male is in the treatment group? Okay, what's the probability they're in the treatment group? Well, how many males are in the treatment group divided by how many males there are? Is that it? So it's probability D equal 1 given male equals males in treatment divided by total males, right? So that's going to be how many males are in the treatment group? 250 divided by 450. 55%. So there is a 55% chance that that male is in the treatment group, even though he either is D equal 1 or not D equal 0 in the treatment group. He can't, there's no such thing as like being 55% in the treatment group. He either is or he isn't, but I pulled out somebody that's a male, so his propensity score is 0.5. His propensity score is 0.5. That's what a propensity score is. A propensity score is a frequentist measure of how many people of those characteristics are in the treatment group divided by how many people have those characteristics. And that's like, so it's not a Bayesian concept. It's just like it's literally like how many are in divided by how many total. That's all it is. Okay, that's literally the only thing it is. Okay. So what we're going to do is we're going to estimate the propensity score. Yep, you do. You use all the observed character. Well, no, Ishika, you use all of the characteristics that are observed. You use all of the characteristics that are needed to satisfy unconfoundedness. So in that sense, yes, you use all the observed characteristics. Where's the 450 coming from? Okay. Total number of males. How many males are there in the data? 250 in treatment, 200 in control, 250 plus 200, 450. There's only 450 men. Great. Okay. So there's two ways that we're going to do propensity score analysis. You either match it or you weight. Okay. And then you need a standard error. When you do the standard error, there's different ways you do it. You can have parametric ways. You can have bootstrapping. You can have non-parametric ways. You can even do double robust, but we're not going to cover it, but it's in the slides. And all of these estimators, though, they assume unconfoundedness. It's always about lack of overlap. If you have lack of overlap, you can use doubly robust methods to deal with matching bias, just like we did, but I'm just not going to cover it. Okay. So all these methods have bias correction methods. They're just different. The propensity scores use doubly robust methods. You can do it with either one, I think. Not positive how you do. I don't remember how you do it with the inverse probability weighting. You do it with the matching, but I don't remember if you do it with the inverse probability weighting, but you do it with the matching. I think you can do it with either one. But it's not like when you do doubly robust, it's like doubly robust is a way of adjusting for the matching bias, is what you're doing. So here's the definition. So usually it's something like this, although you'll see people do it in different ways, but it's basically, what's the probability I'm in the treatment group given I have these characteristics? Well, if you're doing nearest neighbor matching, you're not going to use doubly robust. Doubly robust comes in with propensity scores. But if you have nearest neighbor matching, you can do the bias correction that we covered, but it's not doubly robust. Doubly robust estimates an outcome regression model, which is in the nearest neighbor matching, but it also estimates a propensity score, which you're not doing. And you're not estimating a propensity score. So it's doing it in two different ways. Okay, so there's the propensity score, and I'm going to skip this right here. So, well, here's a quote. We're interested in estimating the average effect of a binary treatment on a scalar outcome if assignment to the treatment is exogenous or unconfounded, that is, independent of the potential outcomes. Given covariates, biases associated with simple treatment and control average comparisons can be removed by adjusting for differences in the covariates. Rosenbaum and Rubin show that adjusting solely for differences between treatment and control units in the propensity score removes all biases, quote, associated with differences in covariates. Does not remove the biases associated with differences in unobservables. Okay, covariates are describing observables. So that's the thing you always want to remember. All right. There's a theorem that shows that it holds if you have unconfoundedness. They prove in the paper you have an unconfoundedness with respect to the propensity score. So that means you don't need all the covariates once you get the propensity score, and you can do all of your work with respect to the propensity score. And so long as you have unconfoundedness there, it carries over. All right. Okay. Step one, pick your parameter. What are you trying to estimate? Are you trying to estimate the ATT? Or are you trying to estimate the average treatment effect? So like, this is all about choosing the population that you're studying. If you're studying only, like if your question is about discrimination, all right, you want to know what's the effect of discrimination on wages, all right? And you want to know what is the effect. There's different ways of articulating it. You could say, I want to know the effect of discrimination on wages for those people who were discriminated against, meaning I want to know the effect of discrimination for Black people, right? That's the average treated on the treated, which you might think to yourself, well, of course, that's what I'm studying. Well, you could imagine, what if Blacks and whites were both discriminated against? Okay. Even though in reality, we usually say only one of them is. Well, that's the average treatment effect. So it's really, really important for you to start out and be like, which population am I studying? Once you decide on which population that you're studying, you immediately know which of these parameters you're studying. And if it's for everybody, it's the average treatment effect. But if it's just for one of either the treatment group or control group, it's either one of those. Then you estimate the propensity score using logit or probit. OLS will give you propensity scores that are outside the bounds. Probabilities can't be negative or greater than 1. And then you're going to use the propensity score or you're going to use those coefficients to estimate the propensity score. And this is what I just wrote there. If I drew someone from the sample with these characteristics, how many of those are in the treatment group divided by the total number of people with those characteristics? Then you're going to use step 3. Step 3 is estimation. Most common method you will see people use is matching. Okay. Matching is going to find a unit in the comparison group, whether it's the treatment or control. You're going to find a unit in the comparison group with a similar propensity score. You might be matching Black people with white people, but if they have the same propensity score, that's perfectly fine. That's kind of the magic of all this. It's all like, you would think that you're having matching discrepancies, but you're not. If you have common support and you have unconfoundedness, it's like every matching discrepancy is kind of being canceled out because of all of this, like, you know, like basically the logic of that's where the proof is really valuable. The logic of it is like, yeah, you're matching Black and white people, but in fact, they have the identical propensity scores, and that unconfoundedness ends up just kind of evening out on average and carrying down. For the ATT, you only need matches for the treatment group within the controls. For the ATE, you need matches on both sides. A lack of overlap is going to create issues for matching. So there are stratification. I'm going to go right here to the inverse probability weighting. All right, because we're kind of running out of time. So I want to get to instrumental variables. So the inverse probability weighting by Hirano, Embens, and Ritter, they work on the weighting method, the inverse probability weighting method. And what you're going to do is here. So let's just focus on the average treated on the treated. You're not going to match with inverse probability weighting. Instead, what I'm going to do is I'm going to weight every observation by the inverse of the propensity score. It's going to look like this too. Let's say that we're estimating the ATT. All right. We're estimating the ATT. All right. When you're estimating the ATT, think about it for a minute. ATT is this. Expectation y1 minus y0 d equal 1 equals expectation y1 d equal 1 minus expectation y0 d equal 1. Okay. We're missing this one. We're not missing that one. Okay. So we can just go like this. We can go, okay. By the switching equation, I have that value. So I don't need to do anything about that. That's correct. It's this one I don't have. So what you're going to do is you're going to use the inverse of the propensity score and weight the D equal 0 units for whom we have Y0. And that's the idea. Since you have unconfoundedness, remember, since you have unconfoundedness with respect to Y0, expectation Y0 D equal 1 equals expectation Y0 D equals 0, which means you can do stuff to the D equals 0 group and recover the missing values for the D equal 1 group. And we're going to weight D equal 0 units. That's what we're going to do. So let's look here. So when we go into this, all right, I'm just going to cover that up. All right, watch what we get. So if that's the treatment group, all of this has to be weighted. So this is the exact formula for the ATT, and it applies to every treatment and control group units. You're going to weight every single observation in the data, but you're only going to weight the outcomes. You're not going to do anything with the covariates. You're just going to weight the outcomes. Why? Because the covariates are in there. And under the propensity score theorem, you don't need the covariates. They're all captured in the propensity score. All right. So you're going to do it. But look, when it's the treatment group unit, it becomes it's going to be like row by row, Eduardo. Eduardo's in the treatment group. I'm going to weight Eduardo's earnings by 1 minus the propensity score divided by 1 minus the propensity score, which is a 1. So I weighted his earnings by 1, which is to say I didn't do anything to him. Okay. Let's say that Sergio is in the control group. Sergio is in the control group. Well, Sergio is getting weight, and it's not 1. Sergio is getting earnings times negative propensity score divided by 1 minus the propensity score. And remember, propensity scores have to be between 0 and 1, which means they cannot be negative. So we just multiplied Eduardo's earnings by a negative value. Why? Why would we weight Eduardo's earnings by negative weights? And the answer is right there. It's the negative. See, what we're doing here is we're using this. That's the Y0 part. All right. That's a Y0 for the control group. So we're bringing it in, but we're needing to subtract it. So that's what that's doing. And we need to adjust for the covariates in order to satisfy unconfoundedness. Okay. All right. Then you get a standard error. You adjust the standard errors. You know, you basically have to get a standard error. You have to adjust the standard errors for that first step. So there's various things that's done. This is work by Whitney Newey and Dan McFadden. You can do a parametric method, you can do a non-parametric method, or you can do the bootstrap. And bootstrap is done a lot. All right, but what if you don't satisfy common support? Well, there's a couple of things that happen. So one of the things, here's the main thing. What people typically do when they don't satisfy common support, they do this. Okay, I got a P-score. All right, so do it again. So I go logit treat. Oh. Okay, so I go logit treat age interaction. Step 1, predict P-score. Step 2, all right, let's see how bad the overlap is. All right, how bad is it though? I didn't see it really good. So let's do it like this. Summarize P-score. All right, so look, the smallest the P-score gets for the treatment group is 0.004, but for the control group, it gets to be like 7 zeros. Yeah, you can, Mashin, you can get it. It's a smooth estimator, which will allow the bootstrap. And so you can do it. For all the propensity scores, you can do it. So you get here the 0.004, but then if you go here, it's 0.00, you got a lot of units. So here we go, watch. Sum P-score if treat equal 1. Count if R men less than, no. Wait. Oh yeah, count if P-score, sorry. Count if P-score less than equal to less than and treat equal 0. I have 504 observations in the control group with propensity scores less than these guys. Okay. Now let's see how many in here have propensity scores greater than these guys. So we're going to go sum P-score if treat equals 0. Count if P-score greater than R max. And treat equal 1. Got 73. All right, I got 73. So what people will sometimes do is they'll just drop those guys. They'll just drop them. They'll say, drop anybody whose P-score is not on the common support. And they'll just, what's called trim the data. They'll trim the data. That's called checking for, all right, so you'll trim it. These are these doubly robust methods. I just skipped it. Where did I do it? Okay, but every time you trim, Okay, I'll show you, Eduardo. So every time you trim the data, you're moving away from your parameter, okay? Because you're always trying to find, I mean, if you drop units in the treatment group and you are estimating the ATT, then, you know, you're getting, you know, if you're doing that, you've thrown that data out. So you can't even, you know, you're not even like, you're losing it. So, but people will still do it. So what Crump and Embens and one guy do is they have like a principled method, at least, for doing it. They have a principled way of doing it. And so you just have here a way of just kind of trimming. So you'll just go, all right, drop if p-score less than 0.1, drop if p-score greater than 0.9. And they just do that. But rather than just simply arbitrarily starting to kind of pick some trimming, they just say, trim it on 0.1 to 0.9 if you're going to do it. And if you do that, then, you know, that's what people will do. But that's important for you to keep in mind, is that, you know, as you start dropping units, it is technically the case that you're kind of losing, you're kind of no longer estimating the same thing. All right. So let's look at real quick the question that Eduardo asked. So who's getting the largest weights? So let's say that Eduardo's in the control. He's in the control. His p-score is 0.75. His inverse probability weight is going to be negative. It's going to be, you know, 0, put the negative aside, 0.75 divided by 1 minus 0.75, which is 0.75, 0.25, 3. Okay, 3. So Eduardo's getting a weight of 3, technically negative 3. All right, but let's do Sergio. Sergio's in the control. His p-score is 0.1. Okay, IPW equals 0.1, 0.9, which is 1/9. So who gets the largest weights? For the ATT, Eduardo got the larger weight. Why? Because Eduardo on observables looks like he belongs in the treatment group. He looks like he belongs. But Sergio does not look like he belongs. So Sergio gets weighted down and Eduardo gets weighted up. That's how it works. Sergio, yeah, that's how that thing works. All right. There's a formula for doing the average treatment effect. If you're estimating the average treatment effect, it kind of goes in the other direction. When you're estimating the average treatment effect, I've studied it a little bit, but I haven't got it prepped and I don't quite remember. So, you know, they like impose, it's like some kind of, I don't remember right now, Anna. I'll have to look at it. It's some kind of trick. I can't remember it between it and genetic though, and it and optimal, but they've done a few of them. But I'll try to remember. Okay. I'm gonna skip the doubly robust, but doubly robust, Sergio, I'll just kind of put the slide up. You can have the right covariates, but the wrong model, and you'll have an unbiasedness requires the right propensity score model. So what if you control for the covariates using propensity scores and you controlled for the covariates using a regression model? That's what the concept of doubly robust is. It's basically allowing a person to control for the covariates 2 different ways. And in controlling for it 2 different ways, you only need to get it right one of the ways. But I don't have time to get into it, but I got it in the slides. I'm a little bit behind. So let's take a break. Let's take a break and we'll come right back in 15 minutes. We'll come back in 25 minutes on the hour. All right. Okay. We're going to jump back in. So the matching methods on the propensity score, since we've already kind of like in detail covered matching, the concept is exactly the same. It's just that you don't have to deal with this like multi-dimensional problem the way we did with nearest neighbor matching, because you just have one dimension. It's the propensity score. So you just find somebody that's the closest. The issue is that if you don't have common support, that exact common support holding, which it's much more, it's a little difficult to know, but if you don't have it, then you're going to be matching people who are slightly different from one another, even on the propensity score. And so the question kind of becomes like, you know, well, I'm matching people that are not exactly the same. And the other thing is like, you're matching people that are not exactly this. Oh, sorry, my bad. And you're matching people that are not exactly the same. And so it's like you can kind of look in here and you can say, well, oh, I trimmed it. So like you're like, I trimmed it. And I got the largest value of the propensity score is the same for both groups. And the largest value of the propensity score is the same for both groups. And you say, I have overlap. Well, it's not exactly correct, because overlap would mean that there is someone in both groups with exactly the same propensity score. And you could have, like, you can't really tell with this histogram because it bends and it takes the averages within these intervals. You don't actually know like where these guys are in this, like, you don't actually know how, you don't really know like, okay, in here, what if like there's a bunch of people in the treatment group, like right there, and there's like, you know, big number. And what if there's like a lot of people in the control group right there? And then like, it's all kind of spotty, basically is what I'm saying. So that you're kind of like doing these like weird matches, you know, like, because you're not doing exact matches, even on the propensity score. So like what was developed, and I'm gonna skip stratification matching. I'm just gonna, because we're running out of time and nobody does this anymore. So I'm just gonna cover these two, caliper and radius. So what people will do is they'll like nearest neighbor match, and they'll put some like some requirements on what constitutes a good match. And the requirements, they're not going to be bias adjustment kinds of things the way that we did with nearest neighbor matching. They're not going to be that. What they're going to be instead is they're going to say, well, I'm not even going to let you match. I'm not even going to let you match if you're not X distance from me. I'm not even going to let you match, which is not the same. We didn't do that in inverse probability weighting. Inverse probability weighting doesn't drop anybody. But technically what people would always do is they would like do matching, and then they would do some kind of caliper or radius matching. And none of them, best I can tell, honestly, best I can tell, there didn't seem to be like, it doesn't seem like there was the same kind of like proofs and theorems around doing this. It was almost like kind of just applied practices that people would do. Because every time you drop a unit, period, from the data, you're no longer getting the aggregate parameter that you're chasing in the first place. If you start dropping treatment units, you're by definition not getting the average treated on the treated. Now, how different it is from the average treated on the treated is a different question. But the point is that if you are embracing ignorance and saying, I don't know what these heterogeneities are, I'm going to allow them to be anything, what sometimes is called unbounded heterogeneous treatment effects, you start dropping any of these units, you have no idea where you're going anymore. And if your goal was to get the ATT, the second you drop one, you're off on your own. So all you can really get when you start dropping them is a particular new parameter. Sometimes it's called, what do they call it? Average treatment effect on the overlap. And it's like got a bunch of weird words like that, but you're kind of moving into this realm of like having to settle for a weird parameter that you never sought out to get. And so once you start doing these matching methods and you start dropping them, it kind of does that. So these are like the old ways of doing it, calipers and radiuses. I'm going to skip the stratification. All right. So, and I'm going to skip this Gary King thing, but you've probably heard about it. He does not recommend doing it. So nearest neighbor matching, you find a unit that's close, and then you're going to weight it based on whether or not you're going to weight it based on it's a treatment group or control group. Sorry, if we're doing the ATT, you're going to weight it in the control groups, and then when you weight it, you're going to basically weight it by the size of the units. All right, so here is some elements to learn about matching bias, or about matching in general. If you match just on one nearest neighbor match, you will lower your bias and you'll increase your variance. But if you match on additional nearest neighbors, okay, well, every time you add in more units that are not the closest thing to the treated unit or the target unit, every time you add in more units that are not close to satisfying that common support, then you automatically increase the bias, but you'll decrease the variance. So there's always these like trade-offs that they would discuss in the literature. And then there's also these issues about whether or not you're going to allow a single unit to appear multiple times in the data as a match. So if you match with replacement, that also will reduce bias. The reason is because you're allowing a good unit to be somebody's nearest neighbor match. And if you have to use them over and over, you can use them over and over. But just like we saw with those Abity and Imbens standard error corrections, it's the same thing here. Once you start allowing for units to appear multiple times as a match, you have to account for that, and that will increase the variance mechanically. But if you allow without replacement, then it won't. But allowing without replacement increases the bias. So then there was also this issue about, all right, well, that's about variance, but what about just like, how far do these guys have to be from one another? And the two main ways that people did was they would create limited distances that a unit could be from its match in order to function as a match. But that might sound reasonable. It might sound reasonable to say, well, you can't match with somebody that's more than like 0.05 propensity score units away. And that might sound great. Except that what do you do with the unit what do you do with that unit when nobody is that close? You drop them. And so that was kind of the issue here, is like when you start dealing with this kind of matching, you have these kind of arbitrary decisions that you're making. Because Mawson might say, well, I'm going to choose a distance of 0.05, and Eduardo might say, well, I'm going to choose a distance of 0.001. And there's no there's nothing theoretical. And you let 1,000 people do the identical study with the identical data, and you tell them to do this kind of matching, and they'll choose different distances. Because there's no so then you'll get variation in the treatment effect, estimated treatment effect, solely because Eduardo, for some reason, really likes 0.001 and Mawson really likes 0.005. And, why'd one pick one over the other? Who knows? Okay, why they did it. So caliper matching, nearest neighbor matching, puts into the breaks of the algorithm this bad neighbors. Well, it'll never be this big, 0.2 units, but that's gigantic. That's a gigantic, I shouldn't even put that in there. That's I should put 0.002 or something. That's a tolerable maximum distance you're going to allow a match to be. Okay, so it's a one-to-one match that you go through and you say nobody can be that far away. But it's like when it says here it's difficult to know, I'm not even sure if it's possible to know, to be honest. There's no there's not, because it's necessarily dropping all these units and all this stuff. So it's who knows what the right thing is, because it's all going to depend on like unknown heterogeneity in the treatment effects. So it's a little ad hoc. And then radius matching basically draws a line, draws a line. So it looks like this. So it says like, here's the propensity score number line. Okay, so it's like P equal X equals 0 or approximately equal to 0. And this is like P of X approximately equal to 1, right? And I want to match here this unit. Unit 1 has P score, P of X of 0.5512. Okay, dot, dot, dot. And let's say the nearest ones are like over here. I got like, 0.53532. And then I got like 0.57572, right? And I got units actually that kind of like, here's maybe where that is. And I might have units that go all the way to there. There could be units like all over here. All right, there could be units all over here. So radius matching basically says, well, I'm going to grab all of them. Grabs everything. I don't even know why this was invented, but like they'll say take everybody, and it's a 1 to many. I recommend without replacement so that you reduce the bias, but with replacement. Sorry, I recommend with replacement. Yeah, I don't know, Yinju. I mean, this is like such a realm of like people kind of doing their own thing. Any answer I would give would be just as made up. But I do think in principle, when there is no clear theoretical reason to do one thing, you have to do a range of things. Otherwise, it looks like you're cherry picking. So I think like probably what you would have to do is you're like, you would just go, I'm going to use like I'm going to go very small and I'm going to go up. But the thing is, I don't even know how to interpret. I know it doesn't sit right with me. And this is why I kind of do favor the inverse probability weight, because the inverse probability weight has very few decisions that you're doing. It doesn't fall into the criticism that Gary King has made, because Gary King has really criticized this. It can, as you sort of do this, you end up with all kinds of weird stuff that are not visible to the naked eye. And whereas under inverse probability weighting, none of the criticisms that Gary King has made about matching hold, because matching is not the same thing as propensity scores. A lot of people get that confused. They say, well, propensity scores, and then in their mind, they fill it out. They say propensity score matching, because that's like the only thing they've ever heard of. But there's like all kinds of stuff. There's stratification weighting on the inverse probability on the propensity score, and there's inverse probability weighting. And they're not the same thing. And matching itself is not the same thing as propensity scores. So that's what I was kind of saying in the beginning. Given that propensity scores are not popular in economics, economists are very unfamiliar with the whole world of it. And then outside of economics, it's much more common. But what I see amongst, like, at least in the medical journals, when people will do propensity scores, they don't seem to really scrutinize the common support stuff. So, I think you got to do all of it. I don't think it works as well, Merritt. First of all, you would definitely, if you did do that, you would definitely need to address some of this. No, I don't think that would work. There might be a specification that would work, but you would definitely be imposing a homogeneous treatment effects with respect to the covariates if you did that. We're going to see that in just a second with regression adjustment. If it is possible to do it, you would probably have to interact the treatment with the propensity score or something. So even then, but I've not seen anybody do that. And you would have to address this common support. Yeah, I believe that he does. I don't have that prepped and I don't have that, like, I can't answer that off the top of my head. But I know that he has worked with it and but I don't remember immediately how he handled it. He's done a lot on the propensity score in general though. All right. I'm going to skip the Lalone. And what we're going to do now is we're going to talk about OLS. All right, and I'm going to skip this, like the basics of OLS. I'm going to assume you know it. We're going to go here to the core ordinary least squares assumptions. I have 20 minutes before lunch, then we'll take a break. But I think that when you see this material, you're going to be sort of surprised, okay? Because you're going to start to realize that even in the world of selection on observables, nobody's, I'm not, I think that this is probably true. Very few people, even in economics, are aware of the biases of OLS, even under selection observables, which doesn't mean that there's not a hack to fix it, but it does mean probably almost tons of regressions have been assuming things which we're going to show are violated very easily. Okay, so we're going to look here. This is probably, like I said, the most common, this is the most common, OLS model that you'll see. Additive controls. Additive controls. I mean, the OLS model is additive, but what I mean is the covariates are entering in only linearly, okay? You got like run a regression of treatment onto treatment dummy, X, and Z, and that's it, okay? And you could have like X squared, you can have all that stuff, but the point is the D variable is kept alone, okay? It's all by itself. So the question is, separate it out? Because we're just saying that it's more than two variables. It's two variables. It's, it's like age, GPA, okay? So that's what we're looking at. So we go, all right, or it could be age squared, right? It could be something like that. So we're going to say, well, what even is that coefficient estimated? Because when we did it over here, all right, and we ran that regression, okay, we knew, all right, hold on. So see, we knew that the average treatment effect was 2,500, and we knew that the average treatment on the treated was 1977. But when we ran the regression of earnings onto treatment and the covariates, and weirdly enough, it's the covariates that belong. Age squared, GPA squared, the interaction, that's the interaction. When we ran it, we didn't get a 2,500. We didn't get a 1977. Okay? So which average treatment effect parameter is it even trying to estimate? And under what conditions will it get an unbiased estimate of that treatment effect? And then thirdly, is it even possible with OLS to get two separate aggregate parameters? Is it even possible with OLS to get the average treatment effect and the average treatment on the treated? And if so, how would you do it? How would you do it? And see, the reason why this isn't oftentimes covered in econometrics classes or stats classes is because oftentimes we motivate those classes traditionally not with potential outcomes. We motivate them with the regression model. And so we start with the regression model and we sort of interpret this coefficient parameter under various claims like exogeneity, okay? Now, I'm not criticizing OLS because I'm going to show that I'm going to show the specification, which will get an unbiased estimate of the average treatment effect and the average treatment on the treated. It's just, I'm not criticizing OLS. I'm going to be criticizing that model, that specification. And that specification has very strong assumptions. All right. So typically what we assume when we estimate that model, we assume that the mean of the error term is 0 conditional on all the covariates, which is more commonly called in econometrics exogeneity. Now, when you think back to stats, we were not using the word exogeneity. What were we using? We were using the word unconfoundedness. So when I first started studying this, I was constantly doing this. I would say, all right, over here in, yeah, right. But I'm saying here that, what are you talking about, Miguel? Yes, right. I'm criticizing the specification. Okay. But look, so I am, this right here is assuming that the error conditional on these covariates is equal to 0. All right. And that's called exogeneity. In the potential outcomes literature, that word does not appear. Because in the literature, it comes from stats, and regression is not the only, approach. So we used unconfoundedness. Sorry. So Imbens and Rubin discussed it in their book on causal inference. And exogeneity turns out, this right here turns out to be a very strong assumption that contains more than just unconfoundedness. So I'm going to pull out a quote from their book. This is from the 2015 book called on causal inference, but I've just now drew a blank on what the book's name is. Causal inference in biology, or something like that, medical or something. So in many empirical studies in social sciences, causal effects are estimated through linear regression, right? Where typically it is implicitly assumed that not in the sample, but in the superpopulation, it is typically assumed that the average of Y, the potential outcome, equals alpha plus delta plus D plus X, okay? Where some values of the 3 unknown parameters, this, and that, for some values of the 3 unknown parameters, that right here was a measure of the average treatment effect, right, in the superpopulation. Defining the error in this way, we can write down this equation, and it was assumed that the error was independent of D and X, and that was referred to as exogeneity of the treatment in the econometrics literature. The regression function is interpreted as a causal relation. I'm going to look at this equation right here. Okay, look at this equation. Y0 constant coefficient X plus error, Y1, Y0 plus this term. Now look, that's what I did here. Okay, Y0 constant, 15,000. Just the covariates times structural parameters, that's what this was. Plus an error term. And then Y1, all right, the regression function is interpreted as a causal relation in our sense of the term causal, namely if we manipulate the treatment, then the outcome would change in expectation by an amount. Hence, in the potential outcomes formulation, we have this. Y1 was equal to Y0 plus delta. Y1 was not equal to Y0 plus delta plus any more X terms, which is not what I did there. Thank you, Chris. I knew it was that. So look at what I did. I did not do this, but what they're saying is that this regression model assumes independence of the error term with respect to D and X, which gives you that 0 conditional mean assumption. And in fact, that ends up also assuming this, which would be that, which is not what I did. Which is not what I did. So then, because error is a function, given the parameters, we can write this down. And by the exogeneity of the treatment indicator, we can get this right here. And thus, conditional independence holds. Here's the quote, though. However, and this was very surprising when I read this in the book. The book has never sold very well, I don't think. It's a fantastic book, but it does, I don't know, it's not an, I don't, usually what people use is the Mostly Harmless Econometrics in economics as a book, or they'll just use a traditional econometrics book, and this one doesn't get used as much. So it's also volume 1, and I don't think they're ever going to write the additional volumes. So it is kind of, I don't know what's going to happen. So the OLS assumptions, however, the exogeneity assumption combines unconfoundedness with functional form and constant treatment effect assumptions that are quite strong and arguably unnecessary. Let me say that again. This assumption, exogeneity, is assuming that that's not there. And what is that? The exogeneity assumption combines unconfoundedness. There's an example of unconfoundedness with functional form, okay, linearity, and constant treatment effects. Is it expensive? I actually didn't know it. Imbens actually sent me a copy. That was really nice. So I didn't have to buy it, but or I actually had already bought it. But so constant treatment effect assumptions that are quite strong. Constant treatment effects. Constant treatment effects with respect to the covariates. So when you have the correct functional form, all right, it's like I could not get ChatGPT to make this. All right, I was trying to. Well, that's like the example. The bridge does not. The bridge going across is common support. What regressions do when you have the correct functional form, it's like shooting across. You don't need, you can take out the enemy with an arrow, you know, or a catapult. But if you don't have it, why not make a, when you have a misspecified, it's like, you know, you miss. And this was actually quite hard. It still didn't do it right. So here. All right, so here's what we mean. Constant treatment effects and linearity. So most commonly used method is OLS. Let's take conditional expectations. We'll just have one covariate. Let's take conditional expectations. Expectation Y for the treatment group X. Expectation Y. Expectation alpha, just alpha. Expectation delta D. Conditional on delta 1X is just going to be delta. And then that's just going to be 1. All right. That's going to be a 1. And then the X isn't going to matter. So it's just going to be a 1. That's going to be delta in just a second. There it is. I'll go ahead and switch over here. And then expectation beta 1X for the treatment group, it's going to be the mean of X in the treatment group times beta 1. It's a good question, Lynn. It's got to, but I hadn't thought of that. And it's not in the book, but it's got to be true. Because the average treatment effects when you aggregate always assume SUFA. So I bet that was like, I bet you're right. I bet you're right. Because it holds under the, yeah, I think so, but I'm not positive. But I think it would. So then look, concentrate. So I write this down right here. There it is. Okay, so when I take this right here, I get this whole thing, right? That's going to be equal to a 1 because the average of D, if you're treated, is going to just be 1, right? So that's what that was. And then this is just going to be, you know, beta 1 average of X for the treatment group. And then I'm going to do the same thing over here. Alpha, delta, average of D, if D equals 0, 0. Beta 1, average of X, D equals 0, X. Okay? Now what I'm going to do is I'm going to replace Y with Y1. All right? So now what I've got is alpha, delta, beta 1, 1. And the question is the average of the X's different if you're in the treatment group than if you're in the control group? And here it is. Because Y1 is based on the X's and it's based on those. See, so in my data, this conditional expectation and that conditional expectation is not the same. But all that's saying is this. Well, my earnings in a world where I didn't go to college is based on my age. It's got some kind of, concavity with the age based on my high school grade, some concavity with that. And then, the older I am and how I did in high school, they both kind of have an additional effect. But if I go to college, I get, a treatment effect, which is going to be Y1 over that. So I got here, it's got to be based on this. Okay. But what if you think that if you go to college, your age earnings profile is different than your age earnings profile if you're a high school graduate? What if you believe that the returns to unobserved skill that's proxied by high school GPA? What if you think that the returns to that natural innate, ability that's being measured by that GPA? What if you think that has its own impact on college educated workers? Well, that's what it means. Heterogeneous treatment effects with respect to the covariates means that you have covariates operating on Y1 in different ways than it's operating on Y0, which is a way of saying unbounded heterogeneity. And if that's true, when I take the average of Y0 for the control group, because look, some age if treat equal 1, some age if treat equal 0, they're not the same. They're not the same. Okay? So and what it's doing though is that it's going to be affecting, in this example, it's going to be affecting the treatment effects. Why? Because look at what the average treatment effect is. It's just expectation Y1 minus expectation Y0. But I'm using a regression equation to measure it. So I go delta hat equals expectation Y1 minus expectation Y0, which is that term minus that term. Some stuff cancels out. That cancels out. Delta expectation D minus delta expectation D, where D equals 0. So that's going to be a 0. So that's going to be isolated right there. Okay, that's going to be isolated. But then I'm going to get this weird new thing here, which is going to be when I run this regression right here, when I run that regression, this coefficient is going to be equal to the average treatment effect plus some unknown coefficient on the average X1 for the treatment group minus the average X0 for the control group, which is the average X for the treatment minus the average X for the control, all the way across the covariates. So that's why they say OLS, in order for this not to matter, you need constant treatment effects. It can't be that the treatment effects vary with respect to these X's, okay? And you're going to need this linearity. So you're going to need homogeneous treatment effects, and treatment effects can't change with respect to the covariates. So what I'm going to do is, we're going to take an hour break. We're going to come back. We're going to finish up OLS. We're going to go into IV. We're going to look at a simulation. We'll spend the rest of the afternoon on IV and try to get caught up as best we can. All right. We're going to try to get caught up as best we can. But let's take an hour break for lunch. Everybody take an hour break, and then we'll start back up. Okay, good. All right, I'm glad. All right, so I'll see you guys in an hour. Be right back. Miguel brings up this this paper here by Timon Stalinsky. I actually did like a 5-part series on that paper. I think it's one of the best papers in econometrics I read that year. I'm not gonna say it's the best paper, but it's definitely one of the best ones that I had read. Where did I put it? I'll go ahead and post it. Well, it's got to get the thing. But anyway, it's this lies, damn lies, and OLS weights, part 5. I went through all this. I've actually got it prepped, but I'm a little worried about time. So his paper's more than just that issue. It has to do with some OLS theorems, but it is a really great paper. So, so this is the assumption. So here's what this means. Okay. So when you are regressing Y onto the treatment in X, okay, which is what we did here. All right. So we know we have 2 parameters in here. These are the actual parameters. The average treatment effect is $2,500. The average treatment on the treated is $1,977. Okay. So we know what the truth is. And when I estimate that regression right there, okay, that regression right there, I am getting $2,500 $2,500 plus coefficients, unknown coefficients on the average mean of the treatment group minus average mean of the comparison group. And that is why that's why it's not 2,500. All of these have different means. Like you can see it. By sort, treat, sum, age, GPA. Those means are different. Okay, those means are different. And so as a result of those means being different by group, biasing it downward. It's biasing it downward, even though unconfoundedness holds, which means even though you're controlling for the correct covariates, and even though you've got linearity, because you do have linearity, because the data generating process is linear, you don't have constant here. You don't have constant treatment effects with respect to the covariates. And so since you don't have constant treatment effects with respect to the covariates, it's pulling it down. It's pulling it, or in this case, it pulled it down. I don't think it has to pull it down because, you know, I don't think we know that, like, it would depend upon the selection on observables, how the X's were related to the treatment and control. But the point is that even with the correct covariates, that is not the correct specification. And yet that is the only specification any of us have probably ever seen anybody do. No, it's not equivalent to attenuation bias because it's biased downward now, but it doesn't have to be biased downward. It all depends upon nature of it doesn't have to do with measurement error. It doesn't have to do with it doesn't have to do with measurement error. It has to do with the fact that the treatment effects differ with respect to the X's, which is what we coded right there. Okay. So let's look at a simulation. All right, let's look at a simulation. So what I'm going to do is I've got here this, so that's called matching RA.do, and this is called HET-TE, heterogeneous treatment effects DE. All right. Now, what I'm going to do is okay. So I have a different deal. I couldn't seed it because I'm going to go through this like 1,000 times or something. Let's see how many times I do it. 1,000 times. So I'm going to run this in the background so that it's like, doing it. I wish I had done the dots. Oh, I am doing the dots. Okay. So it's going to run through it. I'll explain what these are in just a minute. Okay. But we're going to go through a simulation which has a linear data generating process. Which is right here. Okay. Oops. That's your linear data generating process right there. Everything's getting added in. But we're going to have heterogeneity with respect to the covariates, which is modeled with that. And actually, when you're making these simulations, what you've got to do in order to make them is in order for the treatment effects to, on average, equal 2,500, this was the trick I did. I had to demean it because the average of a demeaned variable is going to be 0. So, the average of a deviations from the mean is going to be 0. So that's going to be 0, which is going to cancel that out. That's going to be 0 when I cancel that out. So that's why the average treatment effect is just popping out to be that. But yeah, so we actually have that in our not in this simulation, but I have a whole thing on the stuff that Miguel's talking about of going through the discussion of the heterogeneous treatment effects, but it's probably a solid hour. So what is meant by linear? It means that the underlying data generating process is additive in the controls. So notice it's like y0 is equal to this plus this plus this additive. It's additive. So we're going to have, so it's, it's going to be like, well, I'll show you later a nonlinear data generating process, Ali, just so you can see, okay? So we're going to look at a variety of estimators and specifications. How's it doing? All right, so it's going to take a little bit, but I already have it all loaded up. And the focus is going to be on the estimated average treatment effect and the estimated ATT under a variety of specifications. All right, so here we go. Linear in the parameters, correct? Yes, because you can take it, right. So heterogeneity with respect to X. So heterogeneity with respect to X here. Like I said, so we have two parameters. The average treatment effect is 2,500. The average treated on the treated is 1980. And actually, since I already have done this, this is going to take too long. I might just have to stop it. But it's the same data generating process here. So it's the same one, okay? And we're going to look at 1,000 simulations of the DGP with regression estimates, plotting the coefficient on the treatment dummy. First with age and GPA, and second with the precise model used for Y0. So it's down here. We're going to do this one. Then we're going to do that one. But both of them assume constant treatment effects with respect to the covariates, which is not accurate. All right. And then I have a third one. Misspecified regression model. All right. So then we're going to do that. So here we go. I'm going to run that regression. No quadratics. I'm going to save that coefficient. And then I'm going to run the regression with the longer covariates with all the correct Y0 specification, but no interaction. Yes, the data generating process. All right. So here we go. These are, no, it means that I'm going to get new random draws here. So Y0 and Y1 are changing. This is always staying the same. This is always staying the same. Age and GPA are changing a little bit. They're going to stay with their means and their variances, but the distribution is going to be a little bit different, or not the distribution, but the overall. Okay, good. So I do it. $2,500 is the average treatment effect, The average treated on the treated is 1980. And when I run that regression, okay, when I ran that regression of control for age and GPA, and did I do the, I think actually it's not. So it's only age, GPA, but no quadratics. Did I put that? Yeah, no quadratics. I get on average a 2717, and nowhere in the distribution does it contain the truth. Okay, it doesn't contain average treatment effect because it doesn't contain the average treated on the treated. Then I put in all of the, I mean, it's not the correct specification, but it is, oddly enough, it is the correct specification for Y0. It's just not the correct specification for Y. It's the correct specification for Y0, but I'm not estimating the effect on Y0. I'm estimating the effect on Y. Okay, so I run it, and I still notice how it like moves around, right? I mean, it doesn't have to do that, but notice that it did do that. So here I find it's too large. I find a coefficient that's too large. Now, find a coefficient that's too small. Find a coefficient that's too small. So 3 ifs. If unconfoundedness held, if the potential outcome model was linear, if the treatment effect had been homogeneous with respect to age and GPA, meaning, and what does homogeneous mean? If that had not been there, okay? If college-educated people did not have an additional age earnings profile, then the coefficient on the treatment variable would have been the ATE. Then when I ran that regression, that coefficient would have been $2,500. But it wasn't, because homogeneity with respect to X wasn't true. The Y0 coefficients were not the same as the Y1 coefficients. So why were they biased? Why didn't we have the correct specification? So let's write down a simplified version of the DGP from the code. Okay, Y0 equals X. Y0 equals X, there it is. Y1 equals Y0. Y0 plus average treatment effect, 2,500, plus beta 1x times D. Okay? Beta 1x times D. Notice the setup before x had a different effect on Y0 than it did on Y1. So see, when it's treated, there's an effect of x. Y1. Since it's treated in this situation, okay, you get a different effect of x. So that's the beta 1 would be referring to the 100 or the 1,000, and x would be referring to age GPA. I got one covariate here, all right, times D, because we're only going to be looking at the effect on treated groups. But see, weirdly enough, even though we're only looking at the effect on the, even though, I mean, technically Y1 is true for everybody. It's, this 100 times age plus 1,000 times GPA, it's technically true for everybody. It's just that I only observe Y1 for the treatment group, okay? So take the conditional expectations of the potential outcomes, again, Y1, average treatment effect, that's going to cancel out, that's going to cancel out. There's my delta, all right? There's my delta, and beta 0 x1, beta 0 x1, so that's going to cancel out, that's going to cancel out, and I'm going to get delta plus beta 1 expectation x, treatment group x. And what this is telling you right here is that this will be the regression specification that you want to estimate. This is the regression specification that you want to estimate. Here. If you're wanting to get the average treatment effect and you're wanting to relax that constant treatment effects assumption, but you're still willing to impose that linearity on it, you just don't want to impose constant treatment effects. All it means, okay, all that it means is don't run that regression. Run that one, okay? Run that one. And when you run that one, that will be a 2,500. And if you're wanting to get the average treated on the treated, I mean, it's ridiculous. When you see what you have to do to get the average treated on the treated, you're going to laugh. Okay. But so what you have to do to get the average treated on the treated is funny. But listen, here's the deal. We will estimate two models, once with the simplified but incorrectly specified. It's not technically saturated. It's fully interacted, but I'll explain that at the end, the difference. But I say saturated here. And another with the correctly specified. Okay. So we're going to do the incorrect specification, but interact the treatment with the covariates that we put in. And then we're going to do the correct specification. What's a group? Treatment group? This is only for the dummy. I don't know exactly. I mean, you could dummy them both out, maybe, and saturate both of them. That might work. But let's see. This is called regression adjustment. I hadn't thought about that, but this is called regression adjustment. And it goes back to work by, well, I mean, its history is actually very interesting. It goes back to the 70s. Wooldridge began writing about it. Pat Khaing started writing about it, but it goes back to, and I'm not going to say their name right. It's not Oaxa blinder, the Oaxa blinder decomposition that was used in labor in the 70s to estimate models of discrimination. Oddly enough, it's not Oaxa, but I think it's something else. But Oaxa blinder decomposition is this methodology. All along, they were estimating a causal parameter, but it doesn't really get like I don't really know if it was rediscovered or what, but it doesn't get like brought back into the canon until you got work by Pat Khaing and Jeff Wooldridge that began to really sort of talk about it. And in fact, Jeff Wooldridge's nonlinear difference in differences estimator under staggered adoption, his Moonblock estimator, it's a version of it. It's a version of regression adjustment. So we're going to do it. All right. So first, here's what you have to do. Okay. Misspecified interacted regression model. Kitagawa, Oaxa, and Blinder. Yeah. Kitagawa kind of predates Oaxa and Blinder. I don't know if she was using it to estimate kind of causal. It was like more generally decomposition methods. No, it is not. It is not the parameter of interest. It's used as the parameter of interest, but it is not itself the parameter of interest. The parameter you'll see right now, Miguel. So here first, to get the average treatment effect, when you do the fully interactive, this is not fully, so this is only going to use age and GPA. Okay, it's not the correct specification because even though we've got age and GPA here, we've got to interact. We don't have it correctly specified in the Y0. Nevertheless, I'm going to show it to you. Okay, just so you see how important it is that you get the correct specification. So we have here average treatment effect is going to be the coefficient on beta 1, a coefficient on treatment. All right, coefficient on treatment by itself. Then to get the average treatment on the treated. Okay, so actually, Miguel, you asked, is it the parameter of interest? First of all, it is not itself useful. Second of all, there's two parameters of interest. There is the average treatment effect, and there is the average treatment on the treated. And so you have to make a decision which of those is the parameter of interest. And so what we're just saying here is that to calculate the average treatment effect, it is the coefficient on the treatment dummy. To get the estimate of the average treatment on the treated, you're going to need the coefficient on the treatment and the interactions. Okay, so we're going to get the coefficients on the treatment here, and then we're going to get the coefficients on age, GPA, and because I've got in here an interaction, age, GPA, interaction. So I'm going to save the interaction term, on treat, on GPA, and then the full interaction term. Okay, so there is that right there. Okay, so I got average treatment effect there, and I got beta 1,1 there. No, yeah, I think that is right, Martin. It's primarily, yeah, you have to demean it. That's right. For the algebra to work out, I believe that's right. But but it's not just that. I need to check that. I believe that's right, because I think that that's what's needed for the algebra to work on the interactions. But the point here is not just that, Martin. It's the interaction part too that I want you to also focus on. So I've got here the beta 1, right? So in order to do this, I got beta 1, and notice what else I need. Average covariate for the treatment group multiplied by beta 1, which is here. This. Calculate the mean of the covariates. Take the average of A if you're treated. Take the average of GPA if you're treated. Take the average of the interaction if you're treated. Calculate the ATT. ATT equals treatment plus beta 1,1 for that times the mean. This new beta times the mean of that variable. This new beta times the mean of the interaction. All right? There I did it. And look, still not right, because I don't have the correct model, but it's still not right. But look, it is getting closer to the average treatment effect. Here's the average treatment effect. I got a 2532. It had been 2717. It's still, it's still not within the sampling distribution, but there it is. And then the average treated on the treated, 1746. This is our first time to kind of get close. This is our first time to actually even attempt the average treated on the treated. So now I'm going to do what I call the comically long saturated OLS regression. It's easier to do it here. This is the fully interacted regression model. Okay. So to do it, I'm going to go through and I'm going to regress earnings onto treatment interacted with age squared, GPA squared, and the interaction. Okay. I'm going to save the coefficient on treat called ATE2. Then I'm going to save the coefficients on every interaction, giving me 5 interactions, or giving me 5 interactions and the coefficient on AT. Here, 2, 3, 4, 5, 6. So that's treated, right, by itself, and then 1, 2, 3, 4, 5. So 6 coefficients. Got to save these as scalars now, and then make it a variable. And then what I've got to do is calculate the mean of the covariates. All right, calculate the mean of the covariates for each of the variables, but only for the treatment group. I mean, this is bizarre. If you've never seen this before, you would just think, why have I never seen this before? And, heterogeneous treatment, there's an interesting story in there, and I don't really know the story. It's probably got something to do with the potential outcomes notation. It's probably got something to do with heterogeneous treatment effects, but it definitely has to do with the fact that the regression model that's purely additive that was just like additive in the controls imposed constant treatment effects with respect to those covariates. So we have here's the ATT. And I don't even have a standard error for this, okay? Treat 4, treatment, beta 1, 1 for that, times the average, beta 1, 1 for that, beta 1 for beta 2 for that, times that, beta 3 for that, times that, beta 4 for that, times that, beta 5 for that, times that, okay? If you were to do this manually, if you were to do regression adjustment manually, that's what you would have to do. Unbiased estimate of the average treatment effect. Unbiased estimate of the average treated on the treated. That's what you have to do. That's what you have to do. So the same, and this is what's kind of interesting. What's interesting is I pulled out 2 parameter estimates from 1 regression model. I ran 1 regression model. I just had to use sample means and all the coefficients in a particular way. So notice how the same regression led to both the average treatment effect and the average treated on the treated. That means if you don't state, and this is why the issue of what I said on the first day, you have to say at the start of the project what parameter is the parameter of interest. To use Miguel's language, what is the parameter of interest? And you have to say, is the parameter of interest of the average treatment effect? Because if it is the average treatment effect, it's really straightforward. It's the coefficient on the dummy. And if that's what you want, that's it. But if you want the average treated on the treated, you got to do all this. Well, if you can't identify it, then you can't get it. You're not going to be able to get any. If you cannot identify one of the parameters and you need that parameter to recalculate the average treatment effect or the average treated on the treated, then it, you would not be able to get it. All of this is holding the, I'm imposing unconfoundedness on this. Unconfoundedness, linearity, and I've relaxed head constant treatment effect. So I'm down to just 2 assumptions that are met in the data. They are met in the data. Thankfully, though, here's the great news. You don't have to ever do this. You never have to do this. I don't know if in Python you have to do it. Okay, I don't know about that. But you do not have to do it in Stata, and I don't think you have to do it in R either. Software exists that does this for you. It's called regression adjustment. And in Stata, it's in TFX. You can get the RA, regression adjustment, using TFX. Okay? So this is a quote from that Timon paper that was just brought up. And this is a really great quote. This is a mostly harmless econometrics proof that you can go through. And ordinary least squares is the linear projection of y on D and X. Sorry, the best part here. And it provides the best linear predictor of y given D and X. Okay? Which has to do with regressing y is not the same thing as regressing y0. Okay? What kind of method is it? It's an OLS method. It's regression. It's regression. That's all it is. And it's literally, Cassandra, it is literally the old 1970 whatever Oaxa blinder and the Kitagawa paper from the 50s is it's the Oaxa blinder Kitagawa, if you want to call it that, estimate. All along that was a causal model. And that causal model was estimating the average treated on the treated. But back in the 70s at Princeton, which is where Ron Oaxa, I don't know how to pronounce his name, but Ron Oaxa was a Orley Ashenfelter student at Princeton in the industrial relations section. He developed and what I've heard is that, well, okay, doesn't matter. I did hear Orley had a lot of involvement in it. It was developed without reference to potential outcomes because they didn't learn potential outcomes at Princeton. Josh Angrist, in my interview with him, said he never even had learned potential outcomes at all. He graduated in 1989 out of Princeton. He had never heard of it. He goes to Harvard in the econ department, and then Jamie Robbins introduces Don Rubin's work to him, and specifically the work on the propensity score, and Angrist just eats it up. And then when Embens gets there, they work together and use it. But, you know, I mean, it's like a weird history of thought. I don't mean to get on a tangent, but like, so here we did it. And now I've got all these, okay? So I can just do this myself. So, you know, but what I want to do, so I have no idea why I even took you through that. So let me just kind of show you this. Go into matching. It's called comparison.do. Huh. Maybe it's called comparing. But yeah, this is me doing it manually. Oh, okay. All right. This is me doing it manually. Just in case I want to go back. Okay. So let me show you regression adjustment. All right. So look, here it is. Oh, shoot. I'll do it myself here. Het TE. Okay. All right. So we run that regression. We'll run this regression. Okay. We know the effect is 2,500. We don't get it. Now I'm going to run, okay, when I run all this, when I run the correct one here. Okay, look, if you remember, I'm kind of getting some of those original parameters back. -10, 100, all these things. But look, 2,500. There it is right there. So now I'm going to get the average treated on the treated, run all this. ATT is 1972. 1972. So let's look at, put it in here. Regression adjustment. There it is. All right, let's see what regression adjustment does. Here's the command in Stata. All right, here's the command with Stata. Well, Martin, you don't have to, but the thing is, I just did it to kind of show that. I mean, that's sort of Martin, that's kind of the problem that you're in, is that you don't really know it. So I just fully interacted it, and there were some things that just come out to be a 0 when I did it. So like some stuff, GPA squared, that's a 0. And the interaction, that's a 0 because it doesn't depend on that. Y1 didn't depend on it. But but I just did it so to show you that you know those parameters can be identified, but you know you probably weren't in a overfitting situation by doing it. So TFX, regression adjustment, parentheses, outcome, what you're gonna do the fully interacted thing on, treat, average treat on the treated. 1972, if I go through all this and I don't get a standard error, $1971.561, $1971.561 and you get a standard error. Okay. And so this is kind of interesting because what it's basically doing is it's showing you that there is something out there. I don't have it yet, Eduardo, but we can look for it in just a minute. But I haven't coded this up yet in R. And I'm just sort of this building out of the unconfoundedness part of the workshop has been sort of slow. And I'm still kind of, this is my newest material. Okay. So here we go. If our goal is to conduct causal inference, then the fact that OLS is the best linear predictor of Y is not a good enough reason to use that model, that specification. OLS is best in predicting actual outcomes. Causal inference is about predicting fictional potential outcomes. In other words, OLS is optimal for predicting what is. Instead, we are interested in predicting what would be if treatment were assigned differently. And that's kind of the, it's not that that's the problem with OLS, because there's nothing wrong with OLS at all. But that specification has unnecessarily strong assumptions. And if you have heterogeneity with respect to the covariates, it's not correct. Okay? So now watch. Now let's minimize the average treated on the treated using nearest neighbor matching by minimizing the Mahalanobis distance on age, GPA, polynomials, and interaction. It's one line in Stata, uses one match. In R, the package is matching. Right, okay. So here we go. Here I match on age and GPA. Okay, age and GPA, polynomials, without bias adjustment. Okay, and it's wrong. There's the truth and there's the real effect. But here I put in the estimated average treated on the treated with age and GPA polynomials with the bias adjustment, and it got it right. This is the 1980. It's a slightly different sample. So technically I was only fully interacting. Full saturation would literally be this is where things can get really messy. Full saturation actually interacts the treatment dummy with literally every value of the covariance, yielding a huge number of parameters likely that cannot be estimated, which could get into the stuff you were talking about, Miguel. So regression adjustment with TFX is going to do this for you, but you would have to put in all of those dummies. But note, with heterogeneity, you have to use the fully saturated models to get both average treatment effect and the average tree on the treated. If you've got heterogeneity with respect to every single value, then you'd have to do that. But my DGP did not have that. Okay. But what about, I have a little bit of time. So what if you don't have the correct functional form? All right. So let's say we have a nonlinear data generating process. We've seen what happens if there's heterogeneous treatment effects with respect to the covariates, but that was resolvable, okay, if with this regression adjustment. But Mbens and Rubin note that it's not just constant treatment effects, it's also the linearity. So what we're going to do is we're going to look at the nonlinear matching do file. And I'm not going to do this. So here, let me show you how I do it. Here's how I'm going to generate the nonlinearities. I just made it crazy. All right. Nonlinearities that are going to be a problem for the average treated on the treated mainly are going to come in here. I did it on both, but I did it here. And here's what made it nonlinear. I made it like a, what do they call it? It's like a step function. All right. So Y0 is going to be a random error. If you're in the 25th percentile of age, then it's going to be jump up to a constant of 200 plus a uniform distribution. If it's between the 25th and the 75th percentile, it's going to go down. So that's part of the way that you break the linearity assumption here. So I broke it, go down to 0 plus this uniform distribution. And then for the 75th, I jump back up. So I've got this nonlinear data generating process. And admittedly, I do it over here too. Okay, I do it over here too. So going to make the average, they're going to make the treatment effects. All right. Now it's going to be approximately 15. Think. Yeah. Approximately 15 for the average treatment effect. And it's going to be approximately 272. All right, 264. Because I don't seed the data, because I don't seed it, I can't, like for this, I don't seed it, so I can't actually get it to reproduce. Actually, I'm not very good at figuring out some stuff in Monte Carlos. Anyway, I did that. So here we go. Get our average treatment effect. When I run this regression, I'm not going to do that. Yeah, here we go. Actually, what I'm going to do is I'm going to do regression adjustment. I might actually be able just to do regression adjustment on it. And so if I look back, what was it? It was age, GPA, interaction. Age, so I don't even put in the polynomials. I don't think. Yeah. All right, so I'm going to do it here, regression adjustment. Oh. Average tree on the treated, 380. What was it? $264. And it's not in the confidence interval. Okay. So nonlinear data generating process. What's different? Oh, that's the whole thing. Okay, so here it is, all this like, here's like the regression adjustment by hand. Okay, here's the regression adjustment by hand, the whole thing, which you don't have to do. And now what I'm going to do is I'm just going to do, so that's my point. Sometimes though, if you're requiring linearity, which you are with the OLS, if you are still requiring linearity, even if you do regression adjustment, which does not require constant treatment effects, you can still end up, it'll still be biased because there's three assumptions: unconfoundedness, linearity, and constant treatment effects with respect to the covariates. And we have two of them. With regression adjustment right here, we have two. We do not have all we require. We were able to relax the homogeneous treatment effects. So all we were left with was linearity and unconfoundedness. And this doesn't satisfy linearity. But you know what doesn't require linearity is matching. Matching. So let's run that one. We'll run this one. We'll run TFX NN match earnings age GPA. TFX NN match earnings GPA age. I'm not going to do the correct model. Treat. I think it's N1, NN1. Average treated on the treated. And then we'll do the novice distance. Okay, so we're trying to get the average tree on the tree at 264. And it got it. It actually got it. So I didn't even need to do the bias adjustment, but let's do the interaction. It's a little bit different. 265. Oh, you know why? You know why it didn't matter? I was wondering why it didn't matter. Because in here, there's age. I guess I kind of do have age operating in a little bit through this, but I'm just estimating Y0. So in Y0, I don't really need the bias adjustment. Okay. So look, I was getting TFX in and match earnings age GPA. I was getting it correct, even without the linearity assumption. Even without the linearity assumption. Okay. So I do have in here this very long discussion of Timon's paper, but it's just, I really want to, I'm going to leave you with that to look at yourself. You're welcome to go through these slides. And I want to kind of end now, and we'll go to a break. The last few years in economics, on applied economics and econometrics, in econometrics over the last, I guess, 20 years shifted. I had this interesting interview with yesterday with Bruce Hansen at the University of Wisconsin, the econometrician. And he had this really interesting comment. He said, like, starting in 2000, it was like econometrics really changed. And on a couple of margins, it really changed. One margin was there was actually a larger shift in econometrics that had kind of been happening in the mid 90s because of people like Whitney Newey, Donald Andrews, Jim Powell. And there was changes in the architecture of, this is the first time I'd heard this. And changes in the underlying architecture that was being used for modeling really changed. And as a result, anybody that really knew that architecture was able to make pretty powerful contributions really quickly. And so it was kind of interesting. Bruce went to Yale, studied with this guy, Peter Phillips. And so he had that architecture. So that was one thing that kind of happened. And so he just kind of hits the ground running. It's like big publication. He's just cranking them out, and he does really well. But this other thing that happened, he said, like in 2000, and he said this has been, he thinks so he said, like, that was one of the ways that you could get your citations up. One of the ways you could get your citations up in that period of time was, having those skills, and I can't remember what he said they were, having those skills to work on those areas and do more powerful work. That was one thing. But the second thing was, you can always drive your sites if you work on topics that are valued by applied people. And that's like, because if you just work on pure econometric theory, this is what Bruce said. If you work just on pure econometric theory, it'll be cited by other econometricians, but they're a smaller group of people. But if it can be, both cited by the econometricians and cited by the applied people, then, I mean, it's like, it's a massive, they feed on each other. And so it becomes this massive thing. So, like, last few years has been this like revolution in applied econometrics, precisely partly because of this unique focus on the OLS specifications in causal inference. And the classic one was the diff and diff. That was actually what Bruce said he did too, I think, was time series. And he or maybe that's what Peter Phillips did at Yale, but he, so, like, I think, Nita, what he was saying is that there was a bit of a like shift that happened at that exact time that you're describing. There was a bit of a shift. And so that makes sense. You'll really like this Bruce Hansen interview because it's probably going to help. Not, when you say obsolete, it's like there's a part of that story that he says is kind of happening a little bit. So, like, part of this focus of the last few years has been on OLS specifications, though. In diff and diff, the OLS specification was the two-way fixed effects, where the fixed effects were additive. And Wooldridge came in and did a saturated OLS model and that interacted the treatment with all the fixed effects and recovered the average treat on the treated, doing that extremely elaborate summing. He would circulate these do files for people, and nobody in R people eventually in R did get it because, like, the massive popularity of this diff and diff stuff, everything's been rolled out into R, Stata, Python. But But Jeff ended up working directly with Stata and encouraged people at Stata in Stata 18 to just incorporate it into a new diff and diff suite of packages that included Callaway Santana, as well as Sun and Abraham, as well as his, which was a relief because you saw, I mean, this is kind of the thing. I have this like very long do file, right? That to show, I shouldn't, that was a mistake. But I had this very long do file, right? To do it correctly. That part right there is not hard. What's hard? Correctly doing all these macros was hard, and then doing the summing. You know how I was able to do it? I was able to do it because I went through a trial and error with ChatGPT. I kept going in and doing it over and over again, and I kept forgetting things, or I was taking means incorrectly. You drop one, you get one thing wrong, you get one thing wrong, and right here, you get the whole thing wrong. So it's terrifying. It's terrifying. But thankfully, Jeff has always been really good at pushing these things that he kind of works on, pushing them at Stata. He's a Stata guy. So like he kind of gets them to do it. So that way it's like nobody has to do this manually. Because if you do it manually, yes, it's correct, but the modal person is going to drop one of those coefficients, even though they estimated it correctly, and they're not going to know, and the referee is not going to know. That's the thing. The referee will not know because the sample will look right. And even if they reported the sample averages, which nobody in their right mind would ever do, you still wouldn't be able to do it. So it's just terrifying. Regression adjustment is just so terrifying because there's no way a referee or an editor would even know you made that mistake. But thankfully now you want to use these canned packages as best you can. As best you can. So it turns out, though, this OLS thing was not just a diff and diff problem. It turned out it was like this contamination bias that was associated with multiple treatments and heterogeneous treatment effects. Goldman, Smith, Pinkham, and Hall and Colasar, they show, that paper is, I think, R&R and AER. They show it's a general problem. And we saw it, too, in this. T. Mond's result is bizarre. His OLS theorem, I mean, that OLS model, you would not believe. There's way more stuff under the hood of that OLS specification that you wouldn't believe. It's not just that it's not just about regression. It's not even about regression adjustment. The OLS coefficient is weighting up the wrong groups in the data. So even when you do it, it's still giving you a weird result. So concluding remarks. Unconfoundedness means that the confounders are known and quantified. Means they're in your data and they're well measured, right? And that is itself a major hurdle to get over. Okay, it is something that for some reason in the way that the classes are taught, or the fact that it is the first class that you learn, or it is the fact that you're learning it prior to doing research. Something about it, the way that you learn it the first time, unconfoundedness does not feel difficult. And it is very difficult. Okay? It is difficult in the sense that you have to know that you have selection on observables, which is having a lot of confidence in the knowledge about the data generating process. But let's say you do have it. Well, then you can still identify the treatment effects using matching and weighting and so forth, as long as you have common support. Common support is testable, means you have to scrutinize it, okay? But it's going to fail in finite samples, in which case there are methods that will let you work around common support. Ironically, OLS is one of them. But OLS uses the functional form of the specification to get those coefficients and extrapolate to estimate that missing Y0 or that missing Y0, Y1. That's why you need the linearity. You're going to get those coefficients, fit them, and then estimate the missing counterfactual. Okay? So you lose common support, you can go into OLS, but it's not a free lunch. You have to go to OLS by buying confidence in the functional forms, and those are not testable. All right. So, and it's not even something that your theory would necessarily drive either. So without a prior behavioral model guiding you, it's very hard to defend unconfoundedness. If you want to go in another direction that does not rely upon that extrapolation of OLS, you can use bias adjustment, but it too will have an outcome regression model inside of it. It just won't be a, yeah, you'll be able to do it. So when should you not use unconfoundedness? If you had to just go away with one thing, okay? If you're just going to go away with one thing, when would it be that I would caution you against using assuming it? When individuals are choosing their own treatments. When individuals are choosing their own treatments, and if it is a treatment that is extremely important, divorce, going to college, having a child, okay? Going to war, civil wars, right? There is unlikely to be any set of covariates where inside those covariate dimensions, you think people are flipping coins. That's what remember, that's what unconfoundedness means. If you are estimating average treatment effects off of covariate adjustment, you believe there is randomness in your data set on the treatments, and the randomness is within the dimensions of X. And if there is anywhere where that is unlikely happening, it is when it is a high stakes treatment and an individual is doing it. Okay? You can defend it in some situations. I've got a project right now where there are 16 prisons. And in the project, we estimate a suicide risk score. Okay? And the prison uses that suicide risk score to identify who is likely to self-harm. And if your score is above a certain number, they get assigned a bunch of inmates that have gone through some training to go sit with them. Only 16 prisons have this program. There's 84 prisons that don't. You can talk to these people and you can figure out why they chose these 16 prisons. And not only can you figure out why they chose the 16 prisons, you also know it's selection on observables. What observable? The score. None of the inmates are choosing to go to a therapist. It's being assigned to them based on observables. So yes, they are picking their score, but it's like they're picking their score in the sense that like there's a bunch of stuff that predicts their score, but not all of it is manipulable. Okay. A lot of it is their pre-sentence charge. So, but you wouldn't say they were picking their score rationally. It's not like rational choice. So that's the thing you want to be really thinking about when you're worried. If you're like, I don't know if I have the DAG. Okay, you're fine. All right. You can't know about the DAG. Right. And so then you have all these covariate adjustments, ideas, those falsifications, so maybe you do it, but then you're still wanting to know, do I really want to go in this direction? And the answer is, all right, if you believe with everything inside you that people are rationally sorting into the treatment because you believe that the treatment, they do it because they think the treatment will help them, that's called a Roy model. It's basically the foundation of economics, and versions of it are probably the foundation of all the social sciences. No matter what you believe about people, even if you believe that they are irrational, probably they do things because they believe this thing is going to work, right? So college attendance, the marriage, the children, the divorce, it is probably, it's a real stretch. It's science fiction almost. It's a real stretch of the imagination to believe that people who are identical on covariates have decided to get a divorce by flipping coins. That is why it's a strong assumption, but there are weaker versions of unconfoundedness, which is maybe they are not flipping coins with respect to Y1, but maybe they were flipping coins with respect to Y0. You're still good. That's a weaker assumption, You don't have to be perfectly rational. It is weaker. It's going to limit which parameter that you can chase after. But frankly, the average treated on the treated lots of times is the parameter of interest. People just aren't used to articulating it. Like when I said that part about you want to know the effect of discrimination, which one do you want to know? Do you want to know the average treated on the treated, or do you want to know the average treatment effect? What would be the average treated on the treated? What is the effect of discrimination on those people who are discriminated against? Which is to say, what is the effect of discrimination on Black people, on women, okay, on minorities? Well, that's an average treated on the treated, and you don't need as much unconfoundedness for it, and you don't need as much overlap. So my opinions, you got to start with the parameter that you're after. And people that just have taken like a regression class, that is the most awkward part of the process. That's the most awkward part of the process, because the regression classes don't use potential outcomes usually. So to build out the regression model, that's why you don't know about this regression adjustment stuff. So, it takes some practice, and that's why you just want to focus on populations. Let the population drive the parameter. And if you care about everybody, it's the average treatment effect. If you care about the people in the treatment group, it's the average treated on the treated. If you're willing to only care about the average treated on the treated, go for it. Okay? All right. Don't ever run this regression again. It requires extremely strong assumptions like constant treatment effects, and you don't have to do it. You do need to have functional form, linearity, but what you might do in your papers, in my opinion, if you're going to do it, what you might do in your papers, probably, okay, I will say this, since this is kind of novel, frontier level stuff, you're probably going to have to do this, first of all, for the sake of the referee, because they're not going to understand. So you're probably going to have to do it, and probably you're going to have to argue in a convincing way, maybe a robustness section or what, that you clearly outline that this model imposes constant treatment effects with respect to X, and you cite Embens and Rubin, and you say it is unnecessarily strong and I'm not willing to do it. So therefore I'm going to go in two directions, one of which I am willing to impose linearity. See, what you're doing is you basically state the assumptions. You say, this is the parameter. I am willing to assume linearity. And here I'm going to do it. I'm going to get the average treatment effect and the average treat on the treated. I'm going to do it. You're going to use something like a canned package to do it. And then you're going to say, but I'm also going to relax the linearity, and I'm going to go over here and use matching or inverse probability weighting, and I'm going to do that one. And I think they don't have to be the same. They do not have to be the same, because if linearity holds and common support does not, you're good. That's the right one. But if common support holds, but linearity does not, the other one will be right. But I'm just kind of giving you a map and a roadmap of what I might do if I was doing this. Okay? Okay. So if you want to estimate something with a regression, I think you go with the route of regression adjustment. No, Nia, I have not seen really very many. I think they're starting. Part of the reason I haven't seen it, I mean, honestly, I think it's like a reason for it. Economists, they don't by and large believe in unconfoundedness in the applied community. And so since they don't really it's not really a bias, but it's kind of like a bias. They sort of at a core self, economists really do as a group strongly believe in rational choice. I mean, it's borderline offensive to an economist to ask them not to believe in rational choice. It's like so deep in the motherboard of our training, we get basically just beaten in our head, that first year of our graduate program. So it's like we it's kind of not really popular to use it. And that means that all this econometrics is kind of like in a bit of a silo at the moment. because other fields don't find unconfoundedness nearly as problematic. Because I don't use it either. I don't have any, I don't use it either. I give my students problem sets to do it. And I require it amongst the master's theses or the undergrads, but you know, I don't have a project where I can think, oh yeah, I believe in unconfoundedness. I guess, maybe for this, but probably not. We're probably going to do maybe for this project, because we are going to do matching. So I really like, and if you are going to use any of the matching stuff, I think you've got to take seriously doing these kinds of bias adjustments, whether it's the doubly robust stuff or this Abedian invens thing. But, part of it is you don't need linearity. It's non-parametric. You don't need constant treatment effects, but you are going to probably have to play around with this bias adjustment. And yeah, exactly. Epidemiology, political science, sociology, psychology, the social sciences as a group don't have nearly the prejudice against unconfoundedness that the applied micro community does have. The econometricians don't have it, because the econometricians, they don't have like a dog. They don't really have a dog in the fight. They're just like, well, this is how it works. That's all it's like, if you're willing to do it, here's what you have to do. But the applied community is just always like these natural experiments for the last 25, 30 years. Because, the thing was, this empirical crisis in labor economics in the 70s, it came a lot of the covariate strategies didn't work at all. Covariate strategies were extremely not good. So there's like a long history of skepticism in the program evaluation community for doing it. And the program evaluation community, that's like the soil that causal inference grew out of. And if you're going to do propensity scores, I think it's time to probably spend some time learning this inverse probability weighting, partly because it doesn't have all these like arbitrary choices that you have to make, like with the calipers and the radiuses. You don't have to do it. And it doesn't require knowing also the true propensity score to get efficiency. So that's kind of the big picture. And if you do propensity scores, you need to do these histograms. You need to carefully scrutinize it. And I think that's not always being done when I see it in the medical journals, because I don't know why, but it doesn't get done. So let's take a break. Let's take a break, 15 minutes, and we'll come back 18, 5, 23. So we'll come back 23 minutes on the hour. I just had two friends come to the door, and I was like, oh, I'll show you. I got this new house. And I was like, oh, I'll show you the new house. And I like walked them through. And I was like, oh, you guys see upstairs. This is where my daughter's bedroom is. I opened it. I saw, oh, the door's closed. I opened the door. My cat's been in there basically all day and all night. Somehow they keep going in there, and they keep somehow figuring out how to close the door. And of course, it had gone to the bathroom like multiple times. So it was just so gross. And so I just had to go throw it in the wash. All right. Anyway, so that story had a happy ending. So okay, so here's what we're doing. We spent a long time, no doubt. We spent a long time on that. But I think that the returns to understanding that material is extremely high, if not critically important, especially getting into just so much of it is just so important. And I just feel more and more that I want to make sure that people um I want to make sure that people um have access to what they need. So okay, I'll look, Akish. I'll try to look. If anybody else finds one, if they could post one, I'll try to find one. No, I mean, doubly robust methods are a description of ways to handle an estimation method accommodates both propensity scores and an outcome regression model. And they're in matching, and but the nearest neighbor matching has a bias adjustment method too. I mean, they're all have real value, and it's not, I don't really know exactly if it's gonna I wouldn't say that. I would just probably say that that the bias adjustments are probably pretty important to deal with that common support problem. And I think that's where I think that is where you don't always see a lot of people really going deep on the degree to which they have a common support problem and then addressing it. Well, Anna says, which one do I use the most? Okay. But I think it's biased, to what I'm about to say. I really like the nearest neighbor matching with bias adjustment that we did. But I think it's partly because I really like Alberto Abadi and Ido Embens. So I think that's part of it. But I mean, I think this regression adjustment stuff, I don't really have some clear way of ranking them. I don't think you can really rank them. The doubly robust, the propensity score stuff depends on the propensity score model being correctly specified. The nearest neighbor matching will have bias, as will propensity scores if you don't have exact matching. And then there's bias adjustment methods. They sort of will deal with some kind of matching related bias, but they'll have some additional assumptions. I think probably if I was to write a paper, I think I would probably have a table that had the inverse probability. I would probably do nearest neighbor matching, inverse probability weighting, and regression adjustment. And I probably wouldn't do propensity score matching, but I would do inverse probability weighting. Maybe get a dog. I'm pretty sure dogs go to the bathroom more, Nita. That's your dog bias is not going to get past this guy. Can you quickly recap? So the average treatment effect is used if you want to know the average causal effect for everyone in your sample. That's what you want to know. You go, think of everything in terms of a population. Okay? If you want to know average treatment effect on average for everybody in the data, even people that are not in the treatment, right? So if you're doing a study about ventilators and their effect on COVID symptoms, if you were estimating the average treatment effect, you would be saying, I want to know the average effect of people that are on ventilators, but I even want to know the average effect for people that are not on ventilators. Well, the people not on ventilators, they're probably doing okay. So, you have to make a decision up front. Do you want to actually know that? Because if you want to know the average effect for everybody in the data, and a bunch of people are like not in the treatment for very good reasons, you could get an unbiased estimate, and it could be if you're not careful communicating, it might be a little bit of a challenge. But the average treated on the treated would be, well, I want to know the average effect of ventilators on people who got on the ventilators, right? So that's like, it's all about which population am I studying? Exactly. Patricia is speaking up. Thank you, Patricia. I'm not having to defend the cat castle. If we just focus on the ATT, what does that mean? Does that mean sample composition? What does that mean, sample composition? Especially sample composition. I'm not positive I understand that, Jiangmin. The sample composition. Do you mean like the overall representativeness of the sample or something? Okay. So Jeff's got a thing. Oh, if we just focus on, what does that mean for? I still don't know what that means though. Lemieux. Okay, that's interesting. Yeah, hey, gosh, if you send that to me, I would love to look at it. Okay, yeah, Miguel's looking at Huber, Martin Huber. Yeah, I think that's right. Martin does do a lot of stuff on this. No, I don't think that's the right way, Anthony. I think it's more like I think it's more like this, okay? Claire, I'm so sorry that happened to you. Um, okay, so like look here. Remember this one? And we were like, there's 12 people, there's 11 people. There's 11 people here. And they all have a response to the drug versus mindfulness, right? And so we have average treatment effects here is a 2. Okay, we have an average treatment effect of a 2. All right. And if that's what you want to know, what is the average effect on everybody, then that's what you would do. You would try to target, you would try to use an estimator that can get after that number. But what if you said, there's a group of people on drugs and there's a group of people not on drugs? So, like, for instance, Edith is on the drug and so is Kelly and Mindy. Well, their return is really large. And then there's like the average treated on the untreated. If you're like saying, well, I want to know what it would have been for the people in the control group had they gone on the treatment. There it's negative. You can imagine all of these are really important, is the thing. All of these have a lot of value. They're all kind of interesting. So there's not like a single, you can't really say like, here is what is the correct method. There it is. Yep, that's the 2011. You can't really say like what is the correct parameter that should be cared about. You have to say, that's kind of your business. It's your business. You get to decide what parameter you care about. Nobody gets to tell you. Nobody gets to tell you that. Okay. So, instrumental variables. All right. So, instrumental variables is the next one. IV.pdf. All right. And we're going to see how much we can get done today. I'm going to give a little bit of some background. All right. Give you a little bit of some intuition. Then we're going to get into some basic estimators. This is not an exhaustive IV class. All right. It's not an exhaustive IV class. And I'm not going to cover marginal. I can't believe I even have marginal treatment effects in here. So I don't cover marginal treatment effects. And I'm not going to cover the covariate stuff, which is stuff by Timon. So I have not done it yet. And actually, I didn't remember putting that in. And then the price elasticity of demand, I'm not going to do it. So probably all we're going to do is these things for sure. And then I might do the data visualization. These are applications and advanced topics. Okay, so let's go ahead and start this. IV. So when would you use instrumental variables? Here we go. When would you use instrumental variables? If you cannot satisfy unconfoundedness. This says the concept of CIA, that's conditional independence. If you cannot satisfy selection on observables / unconfoundedness, all that stuff we just spent a day and a half doing is not going to buy you anything with like certainty. Okay. If you can't observe all the confounders, that means, remember, it was known and quantified confounders. Quantified means you observe it. Known means you know what they are. So like, if you can't do both of them, then you might want to use instrumental variables. And instrumental variables does not require a panel. So, like you don't have to be doing diff and diff. And so that might be something you do. Okay, so, and there were alternative methods that were developed. They themselves also have specific instances where they are suitable when they aren't. So one popular method is IV. IV is panel data is longitudinal data following the same units over time. And you can estimate causal effects with a panel or longitudinal data set. And, but sometimes you might not have a longitudinal data set, or the assumptions required for the longitudinal data set, you might not feel like you satisfy those either. Okay. So this is at a famous working paper series in economics, doesn't matter what that stands for, but it's like a popular working paper series. It's kind of, you have to be a member of this group. And this is our top journals. And instrumental variables has grown. It used to be like 10% of all of those working papers. And it's just basically almost monotonically. Over 30% of all papers at that working paper series use IV, and 35% use IV in our top journals. So it's very, 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 very popular, very, very common. It's like 100 and something years old. It was invented by the economists. It's one of the only causal methods that you can actually say economists appeared to have invented. It was invented by a guy named Philip Wright, and it was also independently invented by Yale's Cowles Commission. Whereas OLS was invented by Gauss, and then diff and diff was arguably invented by Ignaz Semmelweis in the 1840s, and then John Snow a little bit later. And then regression discontinuity is invented by Donald Campbell, who's in educational psychology. So it's like, I mean, synthetic control was invented by an economist named Alberto Abadi, but IV is, or it's called IV, is one of the few things that the economists contributed to. This like of this causal toolkit. All of econometrics is enormous, but this one's used a lot more generally. So it's oftentimes associated with this natural experiment stuff. And so it goes back to that natural experiment movement at Princeton Industrial Relations section in the 70s and 80s. So it's often associated with it because you're going to use it in a situation where a person might be choosing their treatment. Okay. And that's what makes you skeptical of unconfoundedness. And you're going to sort of have an instrument that sort of assigned some of the people to the treatment, even though they were trying to be rational, it assigned some of the people to the treatment randomly. So it's again kind of got this random element, just like matching did. Matching and IV are actually pretty similar in the sense that both of them have randomness in it. Matching, unconfoundedness, says that the selection of the treatment was based on covariates, and then all remaining variation in the treatment was random. But IV says that the treatment was assigned to people not randomly, but because of an instrument, and the instrument had randomness in it. So they're all kind of like subtly connected, but they didn't have to be any covariates in an instrumental variable strategy. So it'll be like usually like an outside event that you'll rely on that is moving some people into the treatment and some people not into treatment because of some randomization that's captured by this thing called an instrument. It's just that lots of times the natural experiments, like the real natural experiments, they're almost too crazy. They're too big. There's way too much going on. Like tomorrow in the United States is our annual gridiron football, professional football contest called the Super Bowl. And people will sort of treat the Super Bowl as like a natural experiment. So like, it'll be in whatever city it's going to be in. And they'll be like, well, look, there's like a natural experiment. There's like a big event that's happening to this city. Let's look at the effect. Let's use instrumental variables, use this Super Bowl instrument to look at the effect of this on this. And, true, it did like bring a bunch of people in to town, but it also caused a lot of people to stay at home, and it's causing a lot of people to like drink a lot, and it's causing a lot of people to socialize. It's like it sort of does too many things. So instruments rarely are very hard to find too. Good instruments are hard to find, valid instruments. So you have to kind of know what they are. And if you know what they are, you tend to see them more easily. So here's 4 papers of mine that use IV. I was estimating the effect of online sex work on street prostitution arrests using commercial broadband adoption as an instrument for online sex work. That was in the Journal of Urban Economics with Todd Kendall. Estimated the effect of parental methamphetamine drug abuse on foster care and child abuse using changes in meth prices that were caused by shortages of ingredients used to make meth. Use that right here as an instrument for being a heavy user of meth. That was published in Economic Inquiry with Keith Finley. Estimated the demand for meth using that same instrument, which was kind of contained in this, but we had never like just spelled it out. That was in Health Economics, Keith Finley. And then I have a paper that was just accepted. I should probably update this. It was accepted a couple of months ago at the Journal of Human Resources. Estimated the effect of being classified mentally ill in jail on suicide attempts and time spent in jail and recidivism. So I use it a fair amount, actually, but it's not the kind of thing where you go, I want to use IV. Let me use IV. It's not like going to the gym and you say, today I'm going to go to the gym. I'm going to work abs. It's more like, I have a question. Here's the problems in the data. I have an instrument though. It does satisfy the assumptions, I'm pretty sure, or I believe that I've shown it, and then you can use it. It's not like you pull a model down. It's more like you have the opportunity. So you got to know what that opportunity looks like. So you're going to use it when you have unobserved confounders. You're going to use it when you have reverse causality. You're going to use it with supply and demand models where you have to estimate either supply or demand. You can use it when you have to run an experiment and not everybody obeyed the experimental person to obey their treatment assignment. You're going to use it when you have measurement error, right? There might be some fifth thing I can't think about, but that's kind of like those are at least like the 5 dominant situations. And when you think about it, what even is left? This is the big one. You don't satisfy unconfoundedness. Reverse causality is a big one. Simultaneous equations is a big one. If you run RCTs, that's going to be a big one if you don't have compliance. And then, measurement error will also be one. So this is how I teach it. I teach it this way. So first step is to say that, I want to get the intuition down. Okay. I want to get intuition. I want you to leave where you sort of feel like you understand conceptually what this thing is. Then we'll get into estimation and assumptions, and then we'll get into interpretations. And we're not going to do applications, but we are going to do, because I'm not going to do these two, but we are going to look at some tips, in my personal opinion. So we're going to start out here assuming constant treatment effects so that we can kind of dive into the simplicity first, and then we're going to go back and do heterogeneous treatment effects. But this heterogeneous treatment effects stuff is actually what Angrist and Dimbens won the Nobel Prize for 2 years ago. They won it with David Card, but they won it for their work on IV. So that's what we'll review some of their work. They wrote like a ton of papers on IV in the 90s. So your data, first thing is instruments are not going to be labeled in the data set. You're not going to download a data set, have like a giant code book, and like skip to the index that tells you where all the instruments are. It doesn't work that way. You're going to have, because it's just like you're not going to have a code book that says which of the variables are bad controls and which ones are good controls. Okay, so it's the research question, and knowledge of the data generating process and mainly the treatment assignment mechanism. That's really the main thing. Knowledge of the treatment assignment mechanism is going to tell you what is and is not an instrument. All right. So you're going to know instruments when you see them usually, because you're kind of going to know their general structure. And then you're going to, when you know their like general structure, which has kind of got like a bit of a storyboard aspect to it, what's going to happen, and especially if they catch your heart a little bit and you sort of kind of get almost obsessed with like how interesting they are, that's really probably what affects a lot of people, is you kind of get intrigued and you like thinking about them. What happens is, as you kind of get intrigued and you learn and you know what they look like, and I don't mean like in the data set, I mean, it's more like stories. Talking to people can help you find them. What happens is you start to notice them. You notice them in events, you notice them in conversations, you notice them in newspaper articles, you notice them interviewing someone. They just are almost staring at you. And the reason why other people don't see them is they don't understand what they are, and they might not be interested in causal effects. Okay. So typically they're random events. All right. That's the kind of the right way. You'll hear people say exogenous, but kind of put exogenous down away for now. Typically they're random events. Okay. But they're random events that are going to be captured with one covariate, and that covariate is highly predictive of the treatment and is irrelevant to the outcome. Okay. So if you want to use an instrument, you have to kind of ask yourself a question like this: is there any random, did anybody get into the treatment group randomly? And secondly, if they did get into the treatment group randomly, is there like, do I know the variable that did that assignment? See, when you say that there was a treatment variable that was determined randomly, think about what you're saying. You're saying that there's an RCT in the data, right? Because you've said that something randomized the treatment. It's just that the randomization is coming from an instrument. All right. So right now we kind of have had we've had kind of like three different treatment assignment mechanisms so far. We had the randomized control trial. We had, let's just say, covariates, or the propensity score. Propensity score is assigning treatment, or covariates are assigning treatment. And now we've got a third, the instrument. And then tomorrow we have the running variable in regression discontinuity design. Everything is about the mechanism that assigns units to treatment. Okay, not the distributional kind of characteristics of the variables themselves. Okay. So what if I told you, here's an example. I call this the strangeness example, right? Or the strangeness principle. I thought that's what I called it. I call it the strangeness principle, but here's an example. So here's the thing. Instruments are strange. You'll know that you have found an instrument if, when you try to explain a particular thing about your project to people, they are confused. That's actually one of the things that makes a good instrument, is that when you try to tell someone something but you leave one piece of information out, they are puzzled. Okay, so here would be an example. All right, I go on Thanksgiving, or thanks. Okay, it's a big birthday party. Right, let's say it's a big birthday party, and at my birthday party, I make an announcement. This would be strange, but let's say I did this, and I said, "Hey, everybody, listen. I want to tell you something that I learned today that I think you're going to find interesting. I ran a regression and of whether or not a mother worked outside of the home. And the regression was simply a regression of whether or not the mother worked outside of the home, regressed onto a dummy variable, as to whether or not the first two children born were two boys, two girls. Okay. So I ran this regression. Work for women onto that or that. Like, so that's what it's going to be. If their two kids are boys, first two kids are boys, or their first two kids are a girl versus boy, girl, girl, boy. Okay. And let's just say he like puts in a, beta X, he puts in some covariates, whatever. He does it without, doesn't matter. He ran the model, he does matching, whatever. Okay. And beta hat is negative, highly significant. And he says, what do you think? Can you think of a reason why this is? Right? And everybody there is smart. They have been to college and they, have worked for before. Maybe they even have kids. But it's not really super obvious why two human beings of the same sex versus two human beings of, opposing binary, of two human beings that are, male, female, would have any relevance on the known determinants of a mother deciding to leave the home and work in the market, right? So maybe they say, are they different in age? And I say, nope, I control for age. And so they like kind of start asking a bunch of questions, and it's like that. So here's the strangeness principle. No one can easily tell an obvious story as to why same first two kids' sex would have any relevance for a woman working outside of the home. So in that sense, the correlation between these two variables is a bit surprising, even to intelligent people. Even to intelligent people with knowledge of the world. Okay? That is why that is going to be why this is a good instrument. This dummy variable ends up being a good instrument, and I'll tell you why. Most parents have, in developed countries, most parents have two kinds of things that determine their how big their family is. Okay. First is they have a stopping rule. They say, I want to have 2 kids. I want to have 1 kid. I want to have 3 kids. I want to have 4 kids. Okay. They have some stopping rule, some target number of kids. Secondly, many people have preferences over the sex composition of their family, of their children. My brother had 2 boys, and he decided to have a third. Rolled the dice. It's 50-50 chance whether you're going to have a boy or girl. So it is kind of random. And the thing that is driving the decision to have a third kid is the randomness of having boy, boy, or girl, girl. For some people who were going to stop at 2, but had a strong desire for to have at least one of each. Okay. The sex of your kids is as good as random. It's about 0.51 probability of having a boy. By the way, it is starting to storm here in Waco. If a disaster happens, we'll figure something out. Okay. I hope that the power doesn't go out, but it never rains in Waco. So anytime it does, I always think it's going to be a storm. But anyway, or like a tornado, hopefully not. So, sex of your kids goes random. So there's a paper by Josh Angris. Josh Angris is almost his entire career was coming up with very ingenious instrumental variables. He used sex ratio of the first two kids as an instrument for family size. Okay? He wanted to know the effect. He wanted to know the effect of family size on whether a woman worked. But family size is something people choose. But he figured out that there was an instrument, that there was a part of the family size that was random. Having twins would be another example. Okay? So on its face, it's puzzling that the first two kids' sex gender predicts labor market participation. If it's the, two boys, two girls versus boy, girl, girl, boy, it's not really clear. So instrumental variables is a strategy that formalizes that strangeness. That's what it does. It basically takes that strangeness, which is to say that that this event that's happening has nothing to do with the outcome. It has nothing to do with the outcome. It has something to do with the treatment. But see, when I did that birthday story, think back to what I did with the birthday story. Oh, okay. I didn't do it. When I went to the birthday story, what did I say? I ran the regression of work onto boy, boy, girl, girl. Work, boy, boy, girl, girl. And I didn't say anything about family size, right? And that's what made it strange. What made it strange is that an intelligent person knows that there's nothing about that that has any relevance for work, but it does have relevance for family size. And if I had said family size and work, they would have understood that. And if I had said, oh man, there's a 50-50 chance I'm about to have a power outage. All right, hopefully not, but we'll figure it out. So if it's family, but the instrument, if I had said that your sex ratio predicted having a third kid, you'd have known. And if I had said family size predicts work, you would have understood. But it's something about saying instrument, outcome, but not saying the treatment that confuses people. And that is what actually makes it a good instrument. Okay. All right. So let's take a break, a 15-minute break. And we're going to come back in 15 minutes. Yeah. Actually, Poppy said, should we use the storm as an instrument? That was the first instrument was rain. The first instrument that was ever used was rain, because rain was considered to be random. All right, so let's come back in 15 minutes and we'll keep going. All right. So that was interesting. So there's I can't answer all of these right now because I walked away. So Anna says, maybe we'll cover this. There was recently a paper against the use of IVs. If I'll should go show it. So I don't know that paper, but it could be this. It could be one of these weak instrument papers. There's even one more specific than this, but IV is like propensity scores in the sense that a lot of people hate it. And it's not, as Miguel kind of says, as an econometrician, I can't imagine it. Where was it published? I think that's kind of the sort of the fault lines is like you know, everything in econometrics, just like and everything in statistics is true. You know, it's because it's like math and statistics. So it's all, you know, if the math and the statistics, you know, are the underlying math and statistics is correct, it's correct. The thing we're going to see is that historically IV was used so poorly, so in such unjustified situations, that it's kind of like got a scorched earth kind of thing to it, just like propensity scores. A lot of people do not believe, as a matter of principle, that good instruments exist. So it's not the econometrics of it. They're kind of like saying, you know, they're kind of a lot of people basically take the position. Yeah, that paper's on weak instruments, but the paper on weak instruments that's by David Lee, McCrary, and I think it's either just them or one other person, the first stage has to have an F of about 105. And so, you know, it kind of ends up being relevant for many practical applications. But I think in general, there is a group of people who simply, as a matter of principle, don't think that it's probably getting used correctly, which is not a statement against IV as much as it is its application. But I don't know if I'd like to see Anna's paper. So I want to look at one more thing to illustrate this concept. I'm not going to play this song. It's by Kanye West. It's from his album Life of Pablo. It's called Ultralight Beam. And a rapper named Chance the Rapper. Yeah, you can do multiple instruments, but I'm not going to cover multiple instruments. I am actually going to cover multiple instruments with regards to weak instruments, and to kind of talk a little bit about the problems that can arise with multiple instruments if some of them are weak. But most of what I'm going to do for the sake of time is kind of then move more directly into the binary instrument, binary treatment, which is sort of the classic situation. So Chance the Rapper comes on the song and he sings the following two lines. He says, "I made Sunday candy. I'm never going to hell. I met Kanye West. I'm never going to fail." Okay. So the question is, imagine that imagine that Chance the Rapper comes to you and says, "I made Sunday candy. I'm never going to hell." You, even if you had a religious background, okay? Even if you had a religious background, if you heard him make that argument, if he was being serious, not just singing a song, if he was being serious and not just singing a song, you would be puzzled. You would say, there's nothing about making a song that has anything to do with religion and the afterlife, right? So there's a bit of a puzzle between the event and no, it's not. It's Sunday. You know what? I have never one time thought about that. It's actually having sex on Sunday. I'm pretty sure. Oh my gosh, is it communion? That ruins my example. I'm not positive anymore. I don't know. Oh no, sorry. Sunday Candy's the song. Sunday Candy is the song, but the song I don't know. Okay, I'm sorry. I'll find out, Nita, but I do not think that it is about communion. But that's interesting because that does sound like communion. Anyway, I met Sunday Candy. I'm never going to hell. So he made this song. It became popular. It went on and got him sort of famous. And he says, "I'm never going to hell." There is no connection, even to a religious person, between those two things. Okay? He could go talk to an expert on religion, or he could even go speak with, I mean, imagine just for the sake of argument here, imagine an expert on hell, right? Yeah, he did meet Taylor Swift, and he was very rude to her. uh Expert on hell, he might say this. There's like, well, there's lots of things that determine hell. There's like, you know, your beliefs, you might say. There might be which religion or something. And then there might be like, faith. And then there might be like behavior. And it's like all this stuff, right? There could be like all this stuff that this guy says, well, I wrote hell, and there's all these things that we know from religion that religions teach cause hell, and none of them have to do with that. None of them have to do with that. Okay? So I'm not saying you're wrong. He's never going to say you're wrong. He's just going to say, he's going to say this. He's going to say, I'm confused. I think it's strange. If that's connected, if in fact Sunday candy is connected to the afterlife, he's like, well, that's news to me because I'm the expert on this topic and literally not a single religion teaches it. Okay? That is, as we said, when there is no obvious connection between the variable and the outcome, all right? It like a logical connection. It's not that they're not correlated. They are correlated. They better be correlated. All right? It's that there's no clear reason that that would cause it. Okay? But what if he said this? See, he became a Christian. So he says, I made Sunday candy, I'm never going to hell. It seems like there's got to be more to this story. So what if this is what's more to the story? I made Sunday candy, and my pastor from when I was a kid heard it on the radio and called me up and said, hey, I heard the song on the radio. Why don't you come down to church? We'd love to see you. He goes to church, and now he's never going to hell. Well, church might be one of the things. And if he says to you that Sunday candy caused him to go to church, kind of randomly causes him to go to church, well, then the expert on hell is going to go, oh, yeah, that makes sense. Because that's like, church is one of the things that does it, right? Like I got a whole chapter on church in my book, the definitive book on hell. I got like one of the chapters is called church. So yeah, and there's lots of reasons people go to church. There's like, do you live next door to a church? Were you born in the church? Was it like, had a pretty building? Did they have like a swimming pool? It's like all this stuff. Swimming pools don't cause you to go to hell. All this stuff doesn't cause it. But yeah, there's lots of stuff that causes you to go to church. And if you told me it's the fact that you're some random guy heard it randomly on the radio, yeah, that's kind of how it works. That's what makes it an instrument. It has no direct effect on the outcome. And it's not related to any of these other things. Okay, so like Sunday candy isn't related. If it's not related, it's not related to your beliefs. It's not related to your religion. It's not related to your faith. It's not related to your behavior, but it is related to church. And if your question is about the effect of church on hell, you can use it. If your question is about faith's effect on hell, it doesn't matter. It's completely irrelevant. If your question is one of these other things, you got to find an instrument for those. So instruments are always very specific, and they have lots of structured restrictions that are associated with them. And finding a good instrument is basically about finding a random event. No, because remember what I did at my birthday party? I ran the regression of work on a dummy for whether or not your two kids were boys or girls. And I said, when I run that regression, they were correlated. they were negatively correlated. They have to be correlated. They have to be correlated. They can't be direct. It can't directly cause it. That's difference. Okay. Cannot be directly causing it. Cannot be one of the determinants. Cannot be one of the confounders either. Okay. So usually this is kind of what's going on. Usually what's going on is that like beliefs cause you to go to church. Religion causes you to go to church. Faith causes you to go to church. Behavior causes you to go to church. And these things cause hell. And so if they are unobserved confounders, you can't identify the effect of church on hell because you got all these unobservables. Yeah, exactly. Exactly. So what you need is, see, what the instrument does is the instrument isolates the causal path. Because look, because the instrument can only get to the outcome. How? Through the causal path. It can't get through the outcome through beliefs, can't get to it through religion, can't get to it through faith, can't get to it through behavior. Why? Because the connection from Sunday candy to hell, church is either a direct mechanism or it's a collider. And you can't move through the colliders. So that's what makes it a good instrument. Makes it a good instrument. Exactly. Yeah, it can't be going through an unobserved error. You're right. An unobserved error correction. No, that's not the right way to think about it. You want to think of it as it's correlated the outcome only through the instrument. But you're not going to be able to that. That's not something that you can test, at least not except under some very special circumstances that are not generally applicable, that probably get overused and misused. But you know, this right here, you know, you'll have Sunday candy, correlated with you'll have Sunday candy correlated with hell for all kinds of reasons. So how are you going to know it's only like this? How are you going to know? And that is part of the reason why people can be really negative about instruments, is they can go, I can't rule this out from this and from that. And the reason is because, you know, the field of economics anyway, it takes a fairly skeptical viewpoint. It takes a fairly skeptical viewpoint about being able to make these strong decisions, strong statements about things they cannot back up empirically, and you can't really rule these out. You can do it with like multiple instruments under constant treatment effects, but that one's not usually where we're working with. So you don't really know. So there's parts of IV that are not testable. There's parts that are testable and there's parts that aren't. And that's one of the things that makes it hard. Is it's not hard mathematically. I mean, it's a ratio, frankly, so it's not even hard mathematically. What makes it hard is logic, or is circumstantial. Do you have the right situation such that that variable that you have is credibly not that situation? Okay. And that is the $1 million question, because if you have an instrument that satisfies this situation, I mean, you're sitting on a lottery ticket, a winning lottery ticket. They're very hard to find, these situations. They're not easy to find. So this is the structure of a valid instrument. This is the instrument. It's highly correlated with the outcome. It has nothing to do with the confounders. It does not directly cause the outcome. If you have either of these situations, if it's got a parent variable, all right, a parent confounder that's unobserved, then, you know, Sunday candy is correlated with hell through the confounder channel, not just through this. Or Sunday candy could also be directly causing the outcome, not be correlated with the confounder. But if it's causing the outcome, that's also a problem, because purpose of IV is actually only to study this phenomenon. The instrument literally does not matter. The instrument is no more important than the coin used in an RCT to study some medical treatment on an outcome. Nobody cares about the coin. Who cares about the coin? The coin's not what the study's about. The study's about the medical intervention, not the coin. The coin is assigning the treatment. But if the coin could somehow independently determine the outcome, well, then you would never know what part was the coin and what part was the treatment. It's the same thing here, okay? Second thing, Kanye West. He writes, I met Kanye West, I'm never going to fail. Now, imagine somebody, a rapper, all right? Imagine a rapper. This would not really be true anymore, because now Kanye West his career is basically over. It's incredible. It's, never has there been in the history of music someone fall that low from that high. Really, I can't even think of, can't even think of a person. It's like R. Kelly kind of stuff. And so he says, I met Kanye West, I'm never going to fail. Well, back, 10 years ago, if a rapper said, I met Kanye West, I'm never going to fail, they would go, yeah, that's awesome, man. I believe it. I mean, that's a great contact to have in the music industry. He's probably going to have you rap on one of his songs, which is what Chance the Rapper is literally doing on this song. He's rapping for like a minute on Kanye West's song. He's going to introduce you to really good engineers, really good musicians. He's going to introduce you to Jay-Z. He's going to introduce you to all these like famous people. It's going to make your career. It's like if somebody said, I've co-authored with Josh Angrist, and now I'm going to get a great publication, right? And you're like, okay, well, I'm not positive that's Josh Angrist bringing the best out of you. It very well may be Josh Angrist carried you in that whole project, right? It's really like, it's not really clear. So what it is. So Kanye West is not a good instrument for whatever it is that Chance is saying. If he's saying he inspired him or something like that, he's not a good instrument, because he's not strange enough. Because when a person hears there's a correlation between success and Kanye West, they're not surprised, because Kanye West can directly cause it. Okay? So you need those kinds of DAG structures, make good instruments. And one of the things that this DAG structure implies is there's a bit of a paradox to an intelligent person that doesn't really have prior knowledge of this DAG. When they hear that this is related to each other, see, this is all they have in mind. They just hear you saying that. They're just thinking about all the things that determine this. And for some reason, if that does not come to mind, if that does not come to mind, they can't figure out why these would even be correlated. It's not even that they're saying it's wrong. It's just that they can't figure it out. And that is a good DAG. But see, that's a good instrument. But this one, it's just got too many other explanations, right? It's too many other explanations. So when you hear an instrumental variables paper, or you're reading an instrumental variables paper, simplify it. Write down the instrument, write down the research question. Draw that. Ask them what the confounders are. If you're in a seminar, don't be a jerk about it. Just say, can you help me understand what the confounders are? What are you worried about? Why can't you just run this regression? Why can't you just do matching? What is the confounders that you're worried about? You really need to make a statement about what the confounders are. And the reason why you have to make a statement about what the confounders are is because you have to make an argument that they're not correlated. You know, you got to make a statement. You got to say something about what those are, because, you know, it's you're using the independence between the instrument and the confounders, the unobserved confounders, as also part of the legitimacy of the design. So, you know, ask people, what is it you're worried about? A lot of the time, there's like a laziness to the IV methods where they're kind of like, they just won't even say what it is they're worried about. You know, they're like, I'm just kind of worried. I'm generally a glass half empty person. That's not enough. You have to say, like, what is the confounder? All right. So I'm gonna Google that. I'm gonna look that up in just a second. So then you can condition on that. Uterit says, what if it's correlated with another observable confounder besides the church? Then you're going to have to close that backdoor path by adjusting for the covariate. There's correct ways and incorrect ways to do it. But for now, Timon has written about it. That guy that we mentioned earlier with the OLS paper, he's got a paper that's revise and resubmit at a top econ journal called Review of Economic Studies, and he kind of writes out, you know, the exact specification for doing it. So there's a few new papers that kind of explore this, but they're all going to be basically adjusting for covariance, adjusting for the covariance. So, and then you just have no other backdoor path between the instrument and the outcome except through colliders that you've not controlled for, and except through the colliders, which you don't control for, and through the direct mechanism. So there's got to be only one mechanism, and any confounders you can close with covariate strategies. So here's the questions you need to be asking if you're using IV. Is the instrument correlated with the treatment? That's very important, as we're going to see. Is it correlated with the outcome? Is there evidence for it? What's the evidence? Yeah. If it's okay, Anna, I'm not going to discuss Erolano and Bond because it's a big topic. But yeah, Erolano and Bond do use past values as instruments, but they're still going to have to satisfy. They're still going to have to satisfy this exogeneity assumption. You know, nothing gets around that. There's just like particular structures to the data that they're able to exploit in that panel that allows them to sort of make that justification. You know, but if it doesn't hold, it doesn't hold. So are there random reasons why the treatment changes? Is the instrument independent of the confounders? Is there any reason that the instrument could be directly affecting the outcome? All right. Okay. So let's look at estimators. We're going to really just focus on walled, two-sample, two-stage least squares. That's it. As Miguel said, it's a massive literature. It's enormous how big IV is. You could definitely teach a semester just on IV. It would be mostly of it would probably be worthless. And then because it would be not particularly useful for a lot of people. Nia says, I'm a little confused about here. Nia says, I'm a little confused while thinking about a research question at what point one should think about looking for the instruments. Well, I mean, let's say Nia, write down your research question as a DAG, okay? And then ask yourself if you could just run the regression without any covariates. If you say that you need covariates, well, if you say you don't need to control for anything, you're basically saying that the variable you're looking at is being randomly assigned. Okay. So then you have to ask yourself, all right, well, it's not being randomly assigned. So if it's not being randomly assigned, then are there covariates I could include that would satisfy the factorial criterion? And if you sort of, I think a lot of situations people will, if they're able to think of all the confounders, they might not be in the data. So you continue to let the research question be the research question. But if there is, you can always draw a DAG. You can always just draw the DAG like this. And you can say, well, that's what I'm interested in right there. That's what I'm interested in. But it's confounded. It's confounded. So then you just go, well, what if there was an instrument? It would look like this. It would have nothing to do with this, and it'd have no way to cause the outcome. Now, what's really going to be helpful is if you're able to find something that is truly random. That's how I found my instrument in my paper that was just published. In this paper here, that just came out, here. Adverse impacts of mental health needs assessments on jail outcomes, evidence from transition age youth and adults. Okay. This paper, I found the instrument by taking this lawyer who was the public defender in the mental health courts in this city, taking her out for tacos, burritos, and Indian food. And all I did was I just continually, asked her over and over and over again. I just kept asking her, not like being bit badgering, but she worked for the mental health courts, and the mental health courts were a diversion program. And in this diversion program, if you were put in the mental health courts, you didn't have to go to jail. They would throw out your charges, prison. They would throw out your charges. So, it was like a big deal. Obviously, people that go into the mental health court are mentally ill, though. So I was kind of trying to figure out, well, why are they getting into mental health court? Like, what is it that's making them? And I knew that part of it was mental health was putting them in it, and mental health was going to have a direct relationship to the outcome I was studying. I was studying whether or not you reoffended. Well, mental health is going to cause that. Mental health is going to also cause you to go to mental health court. And mental health is, poorly observed in the data. So, but then what she told me, then one day I said, well, how do they know that they're mentally ill? How could they possibly, how do you know that someone is mentally ill? There's no like blood test. And she said, well, in the jail, they have a therapist who will meet with the client, the inmate. And she scores them 0, 1, 2, 3. And if they get a 2 or a 3, they come to us. And if they get a 0, 1, they go somewhere else. Well, the score is related to that. The score is proxying for this like unobserved factor. And so I was like, okay. But how do they get the therapist? How do they get the therapist? Are they picking their therapist? Because remember, anything the person picks, you should always be a little afraid of it. She goes, well, no, they basically show up at jail and they alphabetize the therapist. And the first person that comes in on the shift sees the first therapist. And then the second person that shows up, the second inmate that shows up sees the second person, and it rotates. Well, that's random. That's random. The alphabetizing, the lettering of the names of the workers has nothing to do with a person's mental illness. That's basically random with respect to the potential outcomes. And when she told me that, I freaked out. I was interested in that question. What is the effect of mental health court on committing new crimes, committing a second offense? But I didn't have a strategy, but I knew this is the thing this is the thing I was positive about. I believed, and I still believe, very few things in the world work perfectly efficient such that there are no sources of randomization. And especially if something's being done to people, those are the situations where the treatment assignment could have some explanation with a little bit of randomness. So all you got to do a lot of the times is just have like an open mind and, try to just have no prior beliefs about what is assigning this treatment to units. Know what your confounders are, but then just go to stakeholders and ask them. It's that simple, especially with government agencies or firms and things like that. Just try to listen. Use emotional intelligence, take them out, talk to people. It's nothing about, none of this is about the econometrics. All of this is about just listening and trying to understand the treatment assignment mechanism. And if you keep asking, you can't ask anybody what's random. You definitely can't ask them what's an instrument. Because they're like, that's like very weird. So instead, what you've got to do is you've just got to listen and just find different ways and apologize for asking the same question twice. That's why I would always take them out for food. Because my whole thought was, well, I'm about to pay you because I'm going to be asking you to listen to me ask the same question in a lot of different ways. And I don't want to offend you. That was why I did it. And it took me some persistence, but I finally found it. So that they're laying around. They're laying around. But the thing is, the only people that know they're there are the very people that don't care about them and don't estimate causal effects. The head public defender in the mental health court is not estimating the causal effects of mental health court on recidivism. They're not. Okay? But you can. All right. Let's take a 15-minute break and we'll come right back. Let's take a 15-minute break and we'll come right back. All right, we'll go ahead and start now. We're going to wrap this thing up and get as far as we can on a day. And we'll kind of finish it up in the morning. All right. So there are two broad approaches in instrumental variables. All right. So there's like family of IV estimators. Over here, there's these methods that are called minimum distance. And then over here, there's these methods that are called two steps. All right. And the minimum distance one is called limited information maximum likelihood. It's a really old one. I think it might be I don't know if it's the first. I read a history and now I've forgotten it, but it was definitely one of the old ones because it was developed by the Cowles Commission. And so it's really old. Okay. Then there is, but it was developed partly for reasons that are like not relevant anymore, which was, it was like computationally fast. And that's like, when you were having to invert all these matrices and things like that, stuff got really, really difficult to do with those back in the 40s and things like that. So these kinds of things that could go faster were really helpful. The two-step ones eventually kind of took over. The liminal does not have the best properties of them out there. Hold on. It's my daughter. So then the two steps end up being more widely used, and that's actually the only thing I've really seen more commonly is to do and that's how most people think. Most people think of IV in terms of doing two different things, and then combining them. So it's like the two steps would be things like walled estimator, two-stage least squares, um, two sample IV, jackknife IV, unbiased jackknife IV, machine learning, or IV lasso. It goes on and on and on. There's just like, there's reverse two-stage least squares, just stuff I've never even heard of. Michael Kolsar at Princeton, he did his dissertation, he did his PhD at MIT under Josh Angrist, and he's got this really big dissertation, and it's in it he develops the unbiased jackknife, which has become really popular, but it's also kind of reads like a giant like definitive book on IV too, because it's just like tons and tons of stuff. So that's kind of like the broad family of stuff, and we're going to be working over here with the two steps. But the main one that you really hear about, and that most people probably thought was IV, many people kind of think it is instrumental variables, is the two-stage least squares estimator. It was developed independently by two economists, one guy named Thiel, one guy named Basman. I don't know the full story of the papers, but they kind of independently did it. And it's too big to review. It's too big of an area to review. So that's why I just focus on a few things. Peter Hull at Brown, who's also Josh Anger's student, he teaches an IV workshop here on Mixtape Sessions. He's also done a shift share IV workshop, which shift share is a kind of instrument. He's done one of those workshops. And then this in April, highly recommend that you consider signing up for his design class. It's based on some class he developed at Brown for the PhD students. It's 3 days. I think it's 6 hours. And it's basically, IV and OLS, but starting with causal inference rather than and then kind of exploring these key things. And so it gets into the unbounded heterogeneous treatment effects immediately. And it's kind of the natural progression of all these kinds of econometrics. It's like focusing on the design methods, which is what we've been doing. Okay. But two-stage least squares is the basic IV model. It's the one you mostly see. It's the one that can control for covariates. It's easy to kind of evaluate the strengths of the instrument, but it does have some issues. Particularly, it's got a finite sample bias when you have weak instruments. We're going to look at that. All right, so I've tried to make this kind of synthesized with as much as I can. I might, and I don't remember, switch my example at one point, but I think I basically stick with this example. And the example is here. So we're going to have earnings, and we're going to have schooling. We're going to have ability. We're going to have some error term, V, and then we're going to have an instrument, Z, all right? And so this equation right here is saying that schooling causes earnings, the error causes earnings, ability causes earnings. It's got three things, all right? And we're going to assume that the instrument is correlated with schooling. And then the other thing we're going to observe in just a second, or assume in just a second, is that ability is also correlated with schooling. And so the story goes like this. This is like, for those that don't come from an econ background, this is like a traditional theory of education in labor, which is that this goes back to this guy named Gary Becker in the 50s. And Becker basically said this. He says, school makes workers more productive. That's S. And more productive workers make more money. So that's like S, Y, but it kind of leaves out the productive part. So it's just like raises their productivity. But problem is people choose schooling. They choose how much to get. And higher ability, and ability is like literally to the economist, ability just means like, I don't even know what I'm talking. I don't even like, there's like 1,000 things I could be talking about. It could be anything from like being very conscientious to like, having having good sleep pattern. So you wake up you can get to school on time, to IQ. It's just some kind of to grit. It could be just like anything, but it's just something that some people have. When you have it, you're already more productive. So higher ability makes people more productive. 2, and that means ability causes earnings, A, Y, and higher ability people find school easier or more valuable. So they also are more likely to go or finish school, which means A causes S, which makes it a confounder. And almost always, the way economists define this, the way that they can find it, well, if it's IQ, it's G, but it's meant to be like, it's just kind of like, doesn't really have necessarily a mapping onto that. But I think, right, isn't it right, Ronald? G is usually associated with the IQ studies. But the point here is that like ability, maybe I'm wrong. Is that wrong? For some reason that popped in my mind. Oh, intelligence. Yeah. But it could be like, it could be grit. It could be a lot of things, but yeah, but perfect. Yeah. So it's like, it's something like that, it has a distribution in the population. And if you have the higher levels of it, whatever it is, you're more likely to go to school and you're more productive. And when you're more productive, your earnings goes up, even if you don't go to school. Okay. So what we're going to do is we're going to use this instrument. We're going to use this instrument to estimate the effect of schooling on earnings, but without having this variable. That's the problem, is that we're not going to have ability. It's not going to be in the data set. Oh, is Sargon? I didn't know that. I always thought it was just Thiel and Basman. Oh, that's good. All right, I'll if you find me a site, Miguel, you can do it later. If you find me a site, I would love to see that. Okay, so we're going to use the instrument to estimate the causal effect. Oh, 1953, 1957, though, is Thiel and Basman. So he must come last. But yeah, okay. Does he cite them? All right. So here we go. Okay, so let me put this back up. Let me delete this. Okay. And what I'm going to do is I'm going to write down the covariance equation between earnings okay. I'm going to write this down. And it's 54. Okay, 53. There it is. So I'm going to write down the covariance between the instrument and the outcome. Now remember, just because it's a strangeness principle does not mean they're not correlated. They will be correlated. That's in fact what makes it strange. The fact that they're correlated is what a person finds perplexing. Okay, so the covariance between Y and Z, all right. What I'm going to do is I'm going to use this definition of Y. So when I have here covariance YZ, I'm going to replace Y with that formula on right hand side. Okay. So I'm going to do that. So instead of y, I'm going to have here the formula for y, so it's just that, comma z. And then I'm going to write down the definition of covariance. So covariance yz equals expectation yz minus expectation y expectation z. So that's the formula, okay? And so all I got to do is replace that y with that equation, and then replace that y with that equation, okay? So if y and z are independent of each other, then this expectation just becomes that expectation, and there'll be no covariance. The covariance will be 0. All right, but if they're related to each other, and see they are related to each other here through that channel, then that will not be collapsing to that, okay? So I'm going to distribute each of these terms times z. So I'm going to get, so I skip a step. I should put this in here. But basically, I'm going to get this, expectation alpha z plus expectation delta s z plus dot, dot, dot. All right, so I'm going to do all that. All right, I'm going to do all that here. And then I'm going to subtract out like the common terms. So look what I get here. So this one becomes expectation alpha expectation z plus expectation delta s expectation z dot, dot, dot. Okay, so I get that, right? And I'm going to group them. Now, when I group them, anything that's a constant comes out of the expectation and goes in the front. So the expectation of a constant, yeah, that's fine. The expectation of a constant is equal to the constant, and an expectation of a constant times a random variable is equal to the constant times the expectation of the random variable. So that's why this becomes right here, expectation alpha z just becomes alpha expectation z. And then over here, expectation alpha just becomes alpha expectation z. So see here, that's going to be 0. That's gone. And then I got this over here. Expectation delta SZ is going to become delta expectation SC. So that's that right there. But I got to do the minus, and then I go over here. Expectation delta S expectation Z. And that becomes delta expectation S expectation Z. Well, look, okay? That right there, okay? Look at that right there. That's the definition of the covariance between S and Z. Okay? That's the definition of the covariance between S and Z. So, or that is right there. Yeah, that is the definition of the covariance. So that's what's going to happen here is I'm going to replace that with covariance, SZ. And actually, that happens to the A term. That's going to be a covariance. And that happens to the V term. That's going to also be a covariance. So in fact, all right, if you were to calculate the covariance between Y and Z, you could do it 2 ways. You could calculate it as you could calculate it directly. All right, you could calculate it directly, and that would be expectation YZ minus expectation of Y times expectation Z. You could do that because you have data on earnings and you have data on the instrument. Right? You could do that one. That's one way to do it. Or you could do this way. And what you would need in order to do it is you would have to have that structural parameter. You would have to have data on schooling and Z, which you have, but you don't know what that is. You would have to know gamma, and you'd have to have data on ability and Z, which you don't have. And then you would have to have data on the error term and Z, which you don't have. But if you did have all those things, you could also calculate it directly. It'd be identical to that number right there. Okay? So what I'm going to do is I'm going to divide both sides by covariance SZ. Okay? Let me do it like this. Covariance SZ. I'm only doing it once, but I'm just going to let you see something visually. Look. Covariance SZ divided by covariance SZ is 0. Is 1. Sorry. It's 1. So that's going to cancel out. So the first thing you realize is that when you divide both sides by covariance of SZ, you isolate the causal effect. It's now isolated by itself. I mean, it's contaminated by these, but like it's got separated by an addition sign, and it's got no other, contaminating factors directly on it. Well, here's the other thing. This DAG structure makes several independence assumptions. I don't know if that's the right way of saying it. Number one, notice Z and A are independent. Z, A, independent. And ZV is independent. ZV, independent. Well, if two things are independent, when you calculate this covariance right here, if you type in covariance AZ, it equals expectation AZ minus expectation A, expectation Z. But if they're independent, then the expectation of the product is equal to the product of the expectations. So that is 0, which means that's a 0 and that's a 0. So it doesn't matter anymore that you've divided it, it's gone. And so you end up with a ratio. When you calculate a ratio, and this is what you would literally be doing, okay? This is right here would be literally what you would be doing is you'd be taking expectation YZ minus expectation Y, expectation Z divided by expectation SZ minus expectation S, expectation Z, okay? And that calculation would be the average treatment effect. And that's what instrumental variables does. IV is a ratio of the covariance between the outcome and the instrument, which is called the reduced form. The history of it doesn't even matter. It goes back to the Cowles Commission. They had all these things called reduced forms, and that's where it came from. It just stuck around. It's the ratio of the covariance between the outcome and the instrument and the covariance between the treatment variable and the instrument, which is called the first stage. What we're assuming, Eduardo, let me just real quick. Eduardo asks, doesn't this identify the late? We're going to start out assuming constant treatment effects. So since everybody has the same treatment effect, the late is the average treatment effect. So it's only when you introduce heterogeneous treatment effects that it happens, that you get this particular parameter, okay, called the late parameter, which we're going to talk about tomorrow. All right, so all you got to do is take the ratio. Just take the ratio, calculate that. There's lots of different things you can do. So, so what conditions must hold? Well, two things. First of all, you're going to be dividing effectively by that right there. So that cannot be 0. Okay. Or it cannot be some, statistically small number. It will never be zero in a finite sample. So when you're working with a finite sample, that covariance will never be zero. But in the population, that is a good question. I am hesitant to say yes, Yinju, because it does go back to that early simultaneous equations literature in the early 20th century. So, like, I don't completely know, but I'm trying to think if I heard it anywhere else. And I think that it's just describing a regression of the outcome onto the instrument. That's the most common thing. I want to say in development economics, the term treatment on the treated, TOT, weirdly enough, is the reduced form. It's like I don't even understand why it's the same, why the TOT is the reduced form. My colleague Rebecca Thornton, I'm trying to get to teach a randomized control trial workshop. She's a Michael Kramer student from Harvard. She was one of these first generation randomizers, and she's like my senior colleague. And I said it in a lecture, and she said TOT, and she described it, and it was the reduced form. So was it, or was it the Wald estimator? Anyway, it doesn't matter. Reduced form here is the numerator of the wall of this Wald estimator, and it is the covariance between Y and Z. And so it's just simply it's the strangeness correlation. Actually, it's the strangeness correlation. It's Sunday candy and hell being correlated, or mother working and the number whether or not their first two kids are boys or girls. That's what it is. Okay. So I'll replace it right now. And maybe I don't know why I stick with this. I end up sticking with it to just kind of like collapse everything into one error term. Yeah, I really want to know the history of it. Rebecca doesn't, she comes from the experimental tradition, which does not necessarily use potential outcomes all the time for its motivation. She knows that stuff, but I think like, I don't think it's as rooted, in like required, because it goes back obviously to the 20s. So I don't really get it. It's because treatment on treated is not the average treatment on the treatment effect on the treatment group. So it's kind of strange to me, but I think I just got to sit down and, oh, right. And I bet Vernon Smith is probably not loading it up with potential outcomes on the front. Because, the whole experimental tradition, I don't think they have to do it, because there's not even really a need for it, because in the RCT, there might be heterogeneous treatment effects, but the ATE and the ATT and the ATU are all the same. And so, you don't have to deal with all this sorting and stuff like that. Anyway, yeah, I know. I had dinner with him, and I had my colleague Earl, who was also older, and Earl went to MIT, and like, he went, and like, he went to MIT, and then Vernon went to Harvard. And I remember, and I said, well, were y'all there at the same time? And Vernon was like, no, I'm like 95. And Earl's nowhere near that. And I was like, what? How is that possible? Vernon Smith is like this Nobel laureate, and he's like almost 100, and does not remotely seem like he could possibly be that old. And it's completely weird. I don't know how he managed it, but he does not say, and he's still publishing and everything. Yeah. So you have this, like, we're going to just combine A and V into a single error term, eta, and just kind of rewrite it. And the Wald estimator, as n goes to infinity anyway, as n goes to infinity, that's 0. All right. And as n goes to infinity, that's not 0. And so as a result, this whole thing goes to 0. And so IV is consistent, meaning that in the infinitely large sample, in the superpopulation, or rather in the infinitely large sample, you will get rid of the bias and you will be left with that causal effect. It is not true that it is not unbiased because there's these weird things with these ratios. So this right here in a finite sample, when you take the sample mean and you divide that sample mean by, or that sample covariance divided by that sample covariance, it will not be exactly 0, and there'll be finite sample bias associated with it. Okay, but the size of it, we're going to see in a minute, can be manipulated, but in a way. So walled can be implemented in all kinds of ways. It can be implemented like within the same data set. You just calculate those simple covariances and then divide it. You do that. You could run a regression, get coefficients on Z on the numerator and then the denominator, and take the ratio of that. That'll be numerically identical. But then, or you could be working with two separate samples. And in one data set, you might only have earnings and the instrument, but not the treatment. But then in a second data set, you might have the treatment and the instrument, but not the earnings. Well, since you only need two calculations, you don't have to have them in the same data set. They do need to be the same people, but they don't have to be in the same data set. And that's called two sample IV. That's what Angress did in his job market paper studying the returns to military enrollment on career earnings. He kind of worked with he had one data set that had like the instrument in it, and the Social Security had the earnings. And then in another data set that he was able to match, he knew whether or not they enrolled in the Vietnam, and he knew their instrument. And he was able to do all these calculations off of it. Because if you don't have the two data sets, you'd have to merge them, but you don't even need to merge them. So once we define what IV is measuring, you're going to see why this works. So let's look at this. I'm going to say that this is my causal model. It is equal to 0. It is. This will equal 0. What did I say? So it's not that it's not as n goes to infinity, that numerator is 0. Okay. And it's equal to covariance. It's both of them. It's the sum of both of them. Okay. So we replaced, so like it became, it's basically that. We replaced it with one thing because it's just kind of it's too cumbersome and we don't need it. Well, Petra's talking more about, oh, right. Thank you, Miguel. Petra, reduced form also is used to describe this workshop. So there's structural econometrics and there's reduced form econometrics. And so is that what you're talking about, Miguel? Is that what she's talking about? Or does she also get into the history? Yeah. So there's both. The reduced form concept describes an entire field, which is this design, like causal inference, as it relates to the potential outcomes. But it also applies to the numerator in the Wald estimator too, which can be a little confusing because you're like, how many different ways is there to say all this stuff? So causal model, all right, we're just going to have there, the error term is going to have A plus V. First stage regression, schooling, going to be based on the instrument. Rho is the coefficient. Second stage regression is going to be Y. It's going to be related to fitted values of schooling, which we're going to get into in a minute. That's going to be the second stage regression. And then here's the reduced form regression, regress the outcome onto the instrument. We have a coefficient on the instrument pi from the reduced form, and we have a coefficient rho from the first stage. Okay. All right. So suppose you have a sample of data on Y, S, and Z, right? So for every observation, we assume the data is generated according to this model, right? Such that the covariance between Z and ability and Z in the error term is 0, just like we did over here. Okay? Because those are equal to 0, that's going to be equal to 0 also. But we're going to also assume that that rho term is not 0. That rho coefficient is not 0. So the rho coefficient is not 0, but the covariance between Z and that is going to be 0. All right? Okay. So what I'm going to do is I'm going to calculate the ratio of the reduced form pi, this one. I'm going to run that regression. I'm going to get that coefficient. And, oh, yeah, to the first stage. So here, actually, let me write down the Wald estimator. So here's the Wald estimator, and then I'm going to explain that part right there. Wald estimator, remember, reduced form, first stage. Then what I'm going to do is I'm going to multiply this times variance of Z over the variance of Z, which is to multiply it by 1, which is not to do anything. So I'm going to multiply this whole thing by a 1. And that 1 is going to be variance of Z over variance of Z, right? Now, since it's variance of Z over variance of Z, that changes this numerator to become covariance ZY divided by the variance of Z. And this becomes variance, here it becomes covariance VS divided by the variance of Z. Now, what is that? That right there, covariance ZY divided by the variance of Z, that is the OLS regression equation. That is the definition of the OLS lines. That's the definition of the OLS lines. When you fit OLS, Y onto Z, you get a slope parameter, and that slope parameter is calculated using that equation. And when you regress S onto Z, you get a slope parameter, rho, and that slope parameter is calculated that way. It's a single number, and it's interpreted as a slope parameter, and that's how it's calculated. Well, so that right there is equal to rho, or sorry, is equal, that YZ is equal to pi, but it's pi hat. And then covariance SC divided by the variance of Z, that's going to be rho hat. So the Wald estimator is also the ratio of two regression coefficients. All right, so there it is again. So now what I'm going to do is just focus on here. And I know I go super slow, but look, I'm just going to ignore that. All right, so what I'm going to do here is I'm just going to take rho hat, which is equal to covariance ZS divided by the variance of Z. There it is. And then I'm just going to multiply both sides by the variance of Z so that I get covariance ZS right here is equal to that term times that term. Okay. The reason I'm going to do it is in a minute, I'm going to make a substitution of covariance ZS for that. I'm going to bring it in. And this is like a way that we're showing the properties of, or that we're basically, going from Wald to two-stage least squares. All right, so we're going to take that Wald IV estimator. Now I've changed it. I'm no longer calling it Wald. I'm going to call it two-stage least squares because for what I'm about to do. All right, so I'm going to take this two-stage least squares. So at this point right now, it's still Wald, but what I'm trying to tell you is that Wald and two-stage least squares are actually identical. They're the same thing. Without covariance and dummies on the instrument, they're the same thing. Okay, so covariance at ZY. Okay, what I'm going to do over covariance ZS, what I'm going to do is I'm going to multiply that by one also. Rho hat over rho hat. But look, covariance ZS covariance ZS, and I'm going to replace that with rho hat variance Z. So down here, covariance ZS, replace that with variance of Z times rho hat. So that becomes rho hat covariance ZY, that's what I did up there, divided by rho hat squared variance ZY. All right. That turns out to be equal to this. Yeah, to see it more easily, take this covariance, write it out using the equation before, and it will become that. And if you take the variance of rho hat times Z, you just write out the variance of rho hat times Z, it's equal to rho hat squared times the variance of Z. So what I've got here is I took that numerator and it just moves the constant into there by the definition of the covariance operator. And then I have here the variance of Z, and that squared term just goes in by itself as without the square. And you could see it if you write, it might be in the book. If you just write that out, you'll get this. And if you write that out, you'll get that. So they're equal. Even with that constant term gets deleted. So you're left with that. All right. So look, what is this doing for us? Well, first thing, interestingly enough, look at this. Anytime you see the covariance between two variables divided by the variance of one of those variables, that is a regression coefficient. The expression of a regression coefficient is covariance divided by variance. Okay. So that means this right here is a regression coefficient. So look, here's the schooling. All right, here's schooling. I run the regression. I get the fitted values. That goes away by the algebra of OLS. That just mechanically goes to zero. And I end up with these constants. But if I have this estimated constant and that estimated coefficient, and for every single unit, I say this, I go, okay, Pappy, right? I say, Pappy, here's a constant, plus here's this estimated coefficient. What's your value of Z? And he's like, my value of Z is a 10. And I go, all right, that plus that times 10 is going to be your predicted schooling. And he'll go, well, that's weird. My actual schooling is a PhD. And I go, well, your predicted schooling is a 17. Okay. So your actual schooling is more than your predicted schooling. But then somebody else might go, I'm a high school graduate, but given their value of their instrument, the predicted schooling they get is like, might be to have gone to some college. So you'll do that all the way down. So that's this. So that's what this is. S hat is predicted schooling from a first stage regression. So look, there's that term. There's that thing right there. There it is. So I write it down. And what I'm going to do is I'm going to replace rho hat Z with fitted value of Z, because look, rho hat Z equals S hat, yes, but plus the intercept. But see, the covariance, what's going to happen is that in that calculation, since it's a constant and it becomes expectation of the constant times Y minus expectation of the constant times expectation Y, it deletes. It just becomes a 0. And so you're just left with covariance S hat. The same thing happens down here. So this term is getting replaced with S hat. So now what we have is another regression coefficient. And so what is it? The regression coefficient is the second stage regression. regressing y onto a constant plus fitted value of s. And what you've done is, if the instrument is correlated with schooling but is independent of ability and independent of the error term, then when you run this regression, you'll get a coefficient, and under constant treatment effects, that coefficient is the causal effect. You can use words like the causal effect with constant treatment effects because it's constant. So it's like it's the same for everybody. And here's the proof. There's the proof of me going through the whole thing. So the intuition of it, here's the intuition of two-stage least squares. What you've done with two-stage least squares is you have replaced this endogenous confounded treatment variable with a pure new treatment variable. But interestingly enough, not a single person in the data set, their old value of schooling is equal to this fitted value of schooling. Nobody has the same thing. Everybody has got different values of predicted schooling than their actual values of schooling, but all of the remaining variation in this like predicted schooling, which over predicts and under predicts schooling for every single person, okay? All of the remaining variation is only the random part of schooling. All of the non-random part, all of the confounded, contaminated part of schooling, it got erased. Where? Where did it get erased? There. So when you took that ratio, we just like go back to it. You took that ratio. Okay. It's equal to that. There it is right there. You go through these series of steps, maybe 4 steps, and two-stage least squares, which is based on walled, which is equal to walled. Two-stage least squares is walled. That's how we got here. Wrote it down, did some simple math, some substitutions. We end up with this. We do some substitutions. We get down to here. Then we replace those, the right-hand side with the left-hand side. And then we get right here a two-stage least squares thing, which requires going through 2 steps. Okay? So there's less variation in the data than there is in the raw schooling variable. There's less variation in the data. But the variation that is left is random. It's random. Which is, so that means you've kind of swept out of your treatment variable all the parts of the treatment that were capturing spurious, parts of it. But the parts that are left are random. And if they're random, remember what randomization does. Randomization allows for selection bias to be equal to 0. That's what it does. It deletes selection bias. Okay. But it can have, in a finite sample, bias. All right. It's consistent, meaning in the infinitely large sample, it's equal to the treatment effect, but in the finite sample, it will be biased. Okay, because of that numerator divided by that denominator, it's like you get some small number divided by something else, and it might not necessarily, be 0. All right, so because in a finite sample, the covariance is never 0 of anything. It's like it's just never is. So what we have instead, all right, so we're going to do this. So what I'm going to do now is I'm going to work with the finite sample. This is the population, and I'm going to replace the covariance with the summation operator. And I'm going to put in the definition of YZ as in its algebraic expression, and it's the deviations from the mean of this variable times the deviations of the mean of that variable, numerator and denominator. And since that's a constant right there, y bar, since that's a constant, it would basically be like y times deviations from the mean minus y bar, the average of y, times deviations from the mean. Well, the average of deviations from the mean is 0. Okay? It's equal to 0. So, but the average of deviations from the mean times a random variable is not on average equal to 0. So this will disappear, which is where that leaves us, but that part won't disappear unless that part won't disappear unless that is independent of z. Okay? Which we're assuming it's not. There we go. Two-stage least squares is going to be this. And we plug in y. And what we're left with is the alpha cancels out like we did before. S, this is alpha, this is delta, summation operator, deviations from the mean, times S. So that is, that term here divided by the same thing, it's equal to 1. So when we go down here, two-stage least squares is equal to delta plus this stuff. Okay? Now, eta is independent of z. If it's independent of z, then in the large sample, that'll be 0, but in the small sample, it won't be 0. So there's this bias. So it's small, it gets smaller as the sample size grows. Okay? All right. So two-stage least squares is nice because in addition to being an estimator, I've always found it to be helpful for thinking about IV. Honestly, Eduardo, that's way too small. There are Monte Carlos where you can go up into the tens of thousands and it's still too small. It really depends upon the data generating process. So we have to look at various kind of diagnostic tests, and we'll look at these various diagnostic tests and use that as kind of a guide to know if the strength of the correlation is large enough to drive that bias almost to 0. Can never do it completely, but like approaching 0 in the limit. So what software do you use? The software that you use in Stata, it's IV Regress, two-stage least squares, or IV Reg 28. Usually it's like one of the two. You need to use a canned package. And the reason you need to use a canned package is this. Stata and R, if you ran that regression, it does not know that's a fitted value. It thinks that that's it does not know that you did a calculation in order to fit it, which means you've lost degrees of freedom, and it's not adjusting for it. Okay, so you've got to do a standard error that takes into account that you estimated the treatment variable in a first stage. Okay, so all of them have canned packages. Stata, IV Regress, two-stage least squares, big package with tons and tons of stuff in it. R, there's an AER package, IV Reg. And then Python, it's called linear models, right? And I have all three in the book online, so you can kind of see the syntax, but we'll also share some stuff. But then there's this, so we could stop there and answer questions, because tomorrow we're going to do this weak instrument material. All right, we're going to do this weak instrument material in the morning, but I can answer questions right now. Does anybody have any questions about what we've discussed? I kind of burned through that. I know you're probably exhausted. Anthony's typing. Anna's typing. Anthony. Oh, yeah. Anthony, right. IV reg, high dimensional fixed effects. That would be another one. Yep. That one's using usually, it's usually panel, probably, but I guess it doesn't have to be. It's just a large number of fixed effects. So that's one. Yes. I'll show you. Well, the coefficient, the stronger the instrument's relationship to the treatment variable, the smaller the bias. And so you should see the bias shrinking and the coefficient of getting closer to the true value. That doesn't mean that it's increasing, but it means that it wouldn't say it's decreasing, but it would mean that it's getting more accurate. I'll show you YouTube in just a moment. I'll show you in just a moment. All right, while you're typing that, Anthony and Anna, I'm just gonna real quick show Yinju something, and I'll be right back. I can see what you're typing. So let me just show you where the alpha disappeared. It's a lot easier than it looks. Super straightforward. Here, so we write down covariance YZ, okay, which is equal to expectation YZ minus expectation Y, expectation Z. We replace Y with A plus DS plus GA plus V. So that gives us expectation A plus DS, A plus DS plus GA plus V Z minus expectation A plus DS plus GA plus V expectation Z. And then you're going to get A expectation Z plus D expectation S Z plus G expectation AZ plus expectation VZ, all right, minus all this other stuff. So we're going to do it. And once you get down to here, all right, I'll have to do it right now. So minus expectation, or it becomes A Z. Okay. And let's just like stop there. So this becomes A Z minus A expectation Z minus A expectation Z. That cancels out. It goes to 0. Okay. And so that's where the covariance of a constant times the covariance of a constant times a random variable is equals 0. That's where it is. So it equals 0. So you know you just really have to deal with covariances of the products of random variables. You don't make it real. There's nothing you can do. Ollie, there's not the constant treatment effects is about the real world. You can't control it. If it's true, it's true. So the thing is, constant treatment effects if it is true, prohibits, makes certain models biased, certain model specifications biased, or inconsistent, rather. So you can't like make treatment effects be anything, because treatment effects are the parameters that you're trying to estimate. You don't know what they are. We have in two-stage least squares the same issue of covariance. Do we have in two-stage least squares the same issue of covariance as in the OLS? Yeah, we do. That's actually Lygia, Timon. I wonder if he's already published it. He's done a bunch of stuff on this. When should we not interpret linear IV estimates as late? This is the guy that we were talking about. In this paper, I revisit the interpretation of the linear IV estimate as a weighted average of conditional local average treatment effects. So one way is that you have heterogeneous treatment effects. I focus on a practically relevant situation in which additional covariates are required for identification, while the reduced form and first stage regressions implicitly restrict the effects of the instruments to be homogeneous and are thus possibly misspecified. I show that the weights on some conditional weights are negative. In the IV estimand, anytime the weights are negative, you're usually in big trouble. And the IV estimand is no longer interpretable as a causal effect under a weaker version of monotonicity. The problem of negative weights disappears in the over-identified specification of Angerson-Embids. Over-identified specification is this like saturated model. And in an alternative method termed reordered IV that I also outlined, even if all the weights are positive, IV is the IV in the just identified specification, meaning one instrument and one treatment variable, is not interpretable as the late parameter unless the groups with different values of the instrument are roughly equal sized. I illustrate my findings in an application to causal effects of college education using the college. So basically, it's almost weirdly enough. And let me just give you this. The problem that we were doing with the OLS model, where you have heterogeneous treatment effects with respect to the covariates, and you need to control for covariates. It's the same deal, and it can be really problematic. And so, you know, the thing is, Timon has been working on this kind of like covariate stuff forever, and he's just really cracked open, you know, the box, cracked open what this thing is doing. It's pretty impressive. And I actually interviewed him. So if you go to my podcast, I interviewed him, and it was wonderful. Here. And I thought it was really inspiring because you kind of got an understanding better about like how he thinks and stuff. But anyway, we're gonna stop there. All right. And tomorrow, what we're gonna do is we're gonna do the weak instrument, and we're gonna look at heterogeneous treatment effects and interpretation, and then we'll do some tips on instrumental variables, and then we'll go into RD. Okay. So I know it was a lot, but we're gonna go ahead and stop there, and then I'll post this. It takes about 3 hours. Y'all have a great evening or whatever, wherever y'all are, and I'll see you tomorrow.